Namaskaram. In the last lesson, we finally got the graph of our equation y equal to 5x and therefore the graph of the original experiment of our car moving on a straight road. At the end of that last lesson, we also left off with two interesting questions, which was the start of a deep dive into the mathematics of how we obtain graphs. The first question was regarding the six original points that we plotted, not the line itself, not the graph itself. The first question was just regarding the six original points that we plotted as shown by the crosses on the graph here. Now remember, how did we get those original points? We chose six very specific stages in the original experiment. Timestamps of 0 seconds, 1 second after the start, 2, 3, 4, 5. For each of those time elapsed or those x values, we plugged those x values in the equation y equal to 5x and obtained the y values or the distance traveled by the car after those elapsed times. We put the x and y values on this table. We got our ordered pairs and then we did our whole grid-like movement and we finally plotted those 6 points on the Cartesian plane. When we plotted those 6 points on the Cartesian plane, what we saw was that those 6 points seemed to be perfectly lining up or seemed to be perfectly taking positions, which made it look like they were all forming one straight line or they were all lining up on one straight line. The question is why? How and why? What's the mathematical reason why when I plot these 6 points, they perfectly form or they perfectly line up along one straight line? And what was the second question that we had at the end of the last lesson? Well, once you plot the 6 original points, what we did in the last lesson was, don't worry about anything else. Now just think about Hansel and Gretel. Using Hansel and Gretel, we looked at those 6 points as breadcrumbs or as clues or as hints, and using them we saw that the shape that they were forming or they were showing us was a straight line, and therefore all we did was we joined the breadcrumbs, right? We started from the origin and drew a straight line through the points and obtained this picture. And what we said was, you can completely be sure that all the other stages on the experiment, the original experiment, they will be the different points on the straight line, which means you don't actually have to plot them. If you had taken every single value of x in the experiment, got the value of y by doing 5x, put each of those infinite points on this table and gone and plotted them one by one, the picture that you would get will be this straight line that your Hansel and Gretel gave you, which means you don't have to actually plot them. The straight line that you draw through these breadcrumbs will be the graph of this equation y equal to 5x. Every point on the straight line will match every stage in the original experiment. That's what Hansel and Gretel showed us. The question was, how do you know? Can you be completely sure, mathematically sure, beyond Hansel and Gretel? Can we understand this in a deeper way than Hansel and Gretel as to how we can be completely sure that every stage in the experiment will now lie on the straight line and nowhere else? And therefore we threw ourselves a curveball at the end of the last class. That's why I drew this weird snake-like pattern. What was I trying to say? All I was saying was, well, what if in some weird way, when I actually take every single stage in between of the actual experiment, put them on the table and actually start plotting them one by one, what if when I actually do that, when I see what shape is forming, what if the shape that's formed is this weird snake-like pattern and not the straight line that Hansel and Gretel was saying that would form? What if that's the case? For example, what if it would be a weird situation wherein somehow the 6 plotted points, the 6 original points are on the same straight line, but when I actually plot all the other points, they form this weird snake-like pattern. Some points on this side, some points on this side, some points on this side, and so on. And only those 6 original points somehow on the straight line. What if that is the graph? What if the graph of this equation is this weird snake-like pattern? How can we be completely certain that all the other stages will be on the straight line? This is the second question. So now we will take a deep dive into these two questions and see how we can understand them in a more mathematical fashion in this lesson. So now let's look at why is it that our 6 plotted points A through F indeed lie on the same straight line. Now, a different way of looking at this is, let's look at the diagram over here. Now, one way I can say is yes, A, B, C, D, E and F lie on the same straight line. A different way of saying the same thing is that when I start from point A, think of it now as a journey, think of it as travel. When I start from point A and if I keep traveling in the same direction, I keep traveling in the same direction without changing my angle or without changing my direction of travel. If I keep traveling in the same direction, I will hit B, C, D, E and F. I will hit all the remaining points if I start from A and travel in the same direction. That's just another way of saying that A, B, C, D, E and F are on the same straight line. Now, the reason we frame that this way is will start getting clearer once we start looking at the other diagrams I have over here. I've taken just 3 of the points A, B and C. It can be extended to D, E and F as well. And we see over here, I've drawn them in 2 different ways. The first way is when they are all on the same straight line. Another way of saying same straight line is, well, A, B and C will be on the same straight line if when I start from A and I travel in the same direction, don't change my direction of travel or my angle, and when I do that I hit B and I continue in the same direction, I'll hit C. If that happens, then A, B and C are on the same straight line. Come to this diagram and see something quite different happens. Here what happens, when I start from A, I move in one direction and hit B. But if I continue to move in the same direction as shown by the dotted line here, if I continue to move in the same direction without changing my angle, then I move completely different and I never hit the point C, because in this diagram the point C is in a different position. From B, if you have to hit point C, you have to change your direction of travel. You have to change the angle in which you are traveling from the original angle that you started off at A. So you go in this direction from A to B, and at B you change it to a new direction and then you hit C. When this happens, you can now see the result of that is A and B will be on one straight line, B and C will be on another straight line, but A, B and C will not be on the same straight line. So now this is an interesting approach, because now we have reframed our question to a more mathematically precise question that we can actually answer. Now we realize that if we have to answer the question as to why A, B, C, D, E and F are on the same straight line, the more mathematical way of saying that is, all we have to do is first figure out or first answer why is it that when I start from A and if I continue to move in the same direction without changing my angle, I hit B, C, D, E and F. Why is it that they all hit in the same position without me having to change my direction of travel? If I can find out the answer to that, the result of that is that the result will be all the 6 points will be on the same straight line. So we don't have to answer the question, why are they on the same straight line? We have to answer a more specific question, a deeper question as to why is it that I hit all of these points when I travel only in one direction. If you can answer that, the result of that is that they will be on the same straight line. So now we have a clearer question to now attack. Why is it that the direction of travel or the angle of travel doesn't change? Let's look at this mini diagram. It's a mini version of what's happening here to understand why. So what we're going to look at here is what determines that direction of travel, right? The direction of travel is the key. Why is that not changing? The question now is going to be looked at as, when I go from one point to the other, right? I have to travel in one direction. What are the factors that determine that direction, that determine that angle that I have to travel? For that, let's look at this figure over here. Now, what we have here, I have drawn the same point A, 0, 0, and I have drawn the same point B here, which is 1, 5. I've just drawn it over here. Now we'll use our Cartesian grid-like movement and try to understand how do we get to B from A using the grid-like movement, right? First we'll move along the X, lock the Y, then move along the Y and lock the X and get to B from A. So let's do that. Starting from A is 0, 0. So if I have to get to B, the first step is keeping the Y coordinate or movement along the Y axis locked. Don't move along the Y axis. Start from A and change the X coordinate by 1, right? You have to move 1 unit along the X axis, right? So change the X coordinate by 1. Then what do? You get to this point. When you get to this point, you lock the X position. No more change along the X axis. And now change the Y coordinate or position along the Y axis by 5. In other words, as I go from A to B, what do I have to do? 2 steps, right? First, I change the X coordinate by 1. That is, I move 1 unit along the X axis. Then I stand over there and then I change the Y coordinate by 5. That is, I move 5 units along the Y axis, right? This determines the final position of B. And that is what fixes the direction that you now have to travel from A to get to B, right? The direction that you have to travel from A to get to B depends upon where B is. And what are the factors that determine where B is? Where B is will be determined by how much you move along the X and then how much you move along the Y to reach B, right? And we can see how both those factors are playing a role, not just how much you move along the X, how much you move along the X, as well as how much you move along the Y. And I've illustrated that here with a couple of other examples on the same diagram. Let's take a different hypothetical situation, right? Let's say now from A, I don't move 1 unit along the X-axis. Let's say I only move 0.5 units along the X-axis. That is, I go from here to the mark 0.5. So I've not moved 1. I only moved 0.5. Then the change along the Y-axis, let's do the same 5 as we did last time. So I'm not changing how much I'm moving along the Y. I'm only changing how much I'm moving along the X. Instead of moving 1, I have moved only 0.5. And now you move the same 5 along the Y-axis. So the X coordinate has changed by 0.5. The Y coordinate has changed by the same 5. And what is the result? The result is you don't get to B. You get to another point B dash here. Can you see this is 5 and this is 0.5. It's not B, it is a point B dash, a different position. Since B dash is in a different position, now the direction that you have to travel from A to B dash is along this arrow. It is not the original direction. The direction has changed simply by changing the X movement, right? Keeping the Y movement fixed. And we can do the other case as well. Look at the next line here. Here what I have done is, I have moved from A along the X-axis by the same 1 unit. So the X coordinate has changed by 1 unit. But instead of changing the Y coordinate by 5, I have changed the Y coordinate only by 2.5. And then you see what happens. Where have I reached? I have not reached B. I have reached another point, which again I have called B dash, which is not the same as B, and therefore the direction that I have to travel from A to B dash is along this line marked by this arrow. It's not the original direction. So as we have seen, if you change the amount of movement along the X-axis or along the Y-axis, if either one changes, the final point is at a different location and therefore the direction of travel is different. This is very, very important because now it shows us that what determines the direction of travel from A to B are both factors, 2 things. From A to B, how much is the X coordinate changing by? The change in X. Change is a very, very important theme in this entire lesson. Change in X and the change in Y. Both factors determine the final position of B, and therefore both factors, change in X as well as change in Y, will determine the direction that you have to travel or the angle that you have to travel from A to B. And therefore, this is now going to show us the way as to why these points are on the same straight line. Now, let's look at the first 3 points on our graph. A, B and C. I have shown a dummy version of that over here, and now we can see, thanks to our insight gained from this diagram, why A, B and C will be on the same straight line. Because when I go from A to B, I have to change x by 1 and I have to change y by 5. That fixes B, that fixes this direction. I move along this direction and reach B. Now what happens as I go from B to C? As you can see, it is identical. The same process happens again. From B to C, again x changes by 1 and again y changes by 5. The changes are identical to what happened from A to B. So if the changes are identical to what happened from A to B, the position that C will be in the same way. It will have the same position from B as what B had from A. I'll repeat that. Because the changes are the same, how C will be located from B will be the same as how B would have been located from A. Right? In both cases, x changes by 1, y changes by 5. X changes by 1, y changes by 5. Therefore, the direction that you have to travel from A to B will be the same direction that you will now travel from B to C, because the changes in x and y are identical. 1, 5, 1, 5. So because of 1 and 5 here, you will have this direction from A to B. Now you are at B. Now from B to C, again the x change is 1. The y change is 5, you get C. You will obviously travel in the same direction because the amount x and y, the amount of change in x and the amount of change in y are identical. Therefore, A to B, same direction, B to C, same direction. What is the result of that? The consequence of that is that A, B and C will now be obviously on the same straight line, because you haven't changed your direction of travel as you have gone from A to B and then from B to C. So the result of that, the obvious result of that is that A, B and C will be on the same straight line. Now we can apply that into the diagram here and extend it to the remaining 3 points as well. So A to B, x changes by 1, y changes by 5, that fixes this direction. From B to C, again x changes by 1, y changes by 5, the direction remains the same. Because the direction remains the same, the result of that is A, B and C are on the same straight line. Now we can continue. From C to D, x again changes by 1. Y again changes by 5. Direction of travel remains the same as a result of that, because of which now A, B, C, D are on the same straight line, and you can go ahead and finish the rest, right? From D to E, again x by 1, y by 5. So the direction will be the same, which now means if you combine everything, A to E, everybody will be on the same straight line, and so on and so forth until F. And now by piecing them together like this, we have seen that the reason A, B, C, D, E and F will definitely be on the same straight line is simply because the direction of travel as I go from A to B, B to C, C to D, D to E and E to F, the direction of travel will remain the same. And why does the direction of travel remain the same? The direction of travel remains the same because as I go from one point to the next, the amount of change in X is always 1 and the amount of change in Y is always 5. X changes by 1 and Y changes by 5 from one point to the next, which therefore results in the same direction of travel. Same direction of travel, the consequence is all the points are on the same straight line. So now we know that basically because as I go from A to B and B to C, C to D, D to E and E to F, in each movement the X changes by 1 and the Y changes by 5. That same movement happens in each of the cases, because of which the direction that I travel from A to B is the same as that I do from B to C, C to D and so on. The result of which is that since the direction of travel is the same, all these 6 points are on the same straight line. So we've completely understood it, all well and good. But as always, we always want to improve on all the knowledge that we have gained. Now here we have a slight problem. The problem is, see, this result that we have is in many ways it's good, it's a good first step, but it's a bit of a trap, it's a bit of a rut, because now if I have to understand why these points are on a straight line, on the same straight line, I have to literally go point by point. I have to go in this order. I have to start from A and say, okay, from A to B, x by 1, y by 5. Hence, I go in this direction. Then from B to C, again x by 1, y by 5. So the same direction. Therefore, A, B and C are on the same straight line. Then if I have to involve D, I have to say, okay, from C to D, again x by 1, y by 5, same direction. Therefore, now A, B, C, D are on the same straight line. So if I have to prove that these points are on the same straight line, I literally have to go point by point, A to B, B to C, C to D, and in each of those cases I have to check that the x is changing by 1 and the y is changing by 5. It works, but it's a bit of a rut because you have to literally go from point to point. There's not much freedom in that, right? So we're always looking to see how we can say the same thing, right? Because the fact of the matter is the same. How can we say the same thing in a slightly broader sense, from a bigger point of view, like a bird's eye view? Say the same thing, but in a larger way that does not have you having to literally go from point to point. What do I mean by that? What I mean by that is, say supposing you want to know, you don't want to know A, B, C, D, E, F individually, right? You want to know, tell me why B, C and F lie on the same straight line. So you're asking the same question, but in a bigger way. You're saying, tell me why B, C and F. I'm not interested about D and E. Tell me why B, C and F lie on the same straight line. Now, we can answer that question in our step-by-step kind of a way, right? We can say, from B to C, it's change in X is 1 and change in Y is 5. So B and C, this is the direction. C and D, it's the same direction because the changes are the same. So B, C, D is on the same line. Then involve E. Again, the changes are the same. Therefore, D and E are on the same straight line. Therefore, if you connect it back, B, C, D, E. And then again, you have to go like that step by step and get to F. It works, but it's just too long. It's like one of my lectures. Too long and too repetitive, right? So what you want to do is you want to do the same thing, but I don't want to have to go step by step by step by step. Can I say the same condition, or can I look at the same condition that X is changing by 1 and Y is changing by 5? That gives the same angle. That gives the same direction, right? Can I look at that in a broader way, in a bigger way, so that without having to go point by point, I can in one go tell the questioner why B, C and say F will be on the same straight line without having to go through D and E, right? So this is a very, very important thing that is key to gaining knowledge in fields like mathematics and science, basically gaining real world knowledge about how the universe works. It's a process we call abstraction. Why do we use the word abstraction? Because we start off with very, very small, defined, point by point kind of conditions like 1 and 5, 1 and 5. Then we try to look at the same thing from a bigger view, right? And see what is the general thing that's happening here and try to get a result which is basically the same as change in X1, change in Y5, but in a slightly broader way, in a bigger way that will enable us to understand why B, C and F, for example, will lie on the same straight line without having to go point by point, right? So take what you have discovered, take the facts that you have discovered and try to identify the larger patterns that are playing out, the overall pattern, and see the picture from a bigger sense and try to see what's really happening. This is called abstraction, and this is what we're going to start doing now. So how do we do this abstraction? How do we get a more general condition for why points fall on a straight line? Let's take the example of the 3 points that we've already been talking about. B, C and straight away we'll go to F, right? So now we want to see what is a more expanded, abstracted condition that can tell us in a very simple way why B, C and straight away F lie on the same straight line. Now, if you look at the diagram, you already know for a fact now that B, C and F are on the same straight line. And if you have to prove it in the original way, what I like to equate it to Lord of the Rings, Frodo Baggins going step by step in that long tedious way, we can prove it, right? We can prove why B, C and F are on the same straight line using our original condition. From B to C, X changes by 1, Y changes by 5, that gives this direction. From C to D, it's the same change in X by 1, change in Y by 5, so the direction doesn't change, and therefore B, C, D are on the same straight line. The same thing happens to E, direction doesn't change, therefore B, C, D, E are on the same straight line. You can go point by point, Frodo Baggins, right? Frodo is his name, no? Check once. You can go point by point like that and finally get to F, and therefore say, F, E, D, C, B, A, they're all on the same straight line. That's exactly what we want to avoid now. We want to have a way of getting the same result without having to do Lord of the Rings trip to Mordor, right? So how do we do that? First, let's look at what we have here, and I've drawn a mini version of that diagram over here. Let's see what the changes are in X and Y as we go from B to C and then C to F. Luckily, now we already know that they are on a straight line, right? B, C and F are on the same straight line. So now let's use that to our advantage. Now let's look at what happens as we go from B to C. As we go from B to C, it's the same deal, right? The X coordinate changes by 1 and the Y coordinate changes by 5. No problem over there. What are the changes in X and Y as we go from C to F, right? So I've tried to show that in a more detailed way over here. Let's look at the X movement first, right? How much do I have to move along the X axis, or how much does the X coordinate have to change as I go from C to F? We won't bother about the change in Y. We'll always do one direction first and then do the other one, right? Cartesian plane. So now if you look at point C, its X coordinate is 2, which means the X position of point C away from the origin is 2 units along the X axis. I have shown that 2 here, right? Now if you have to start moving towards F, you have to first change the X coordinate from 2 to 5, right? So basically you have to essentially move along the X axis. You can keep the Y locked. You have to move along the X axis from point C to the 5 mark here along the X axis. So you're going to start from 2 and move to 5. The broader way of saying that is, when you are at C in terms of your position along the X axis, you are 2 units away from the start. The start meaning the origin. You are here when you are at point C, right? And when you move to F, you are actually at 5 units. What does this 5 mean? It actually means 5 from the start, right? 5 from 0. So 0 to 5. This is where you are when you are trying to move towards F. This is at least the X coordinate of F, right? And this is the X coordinate of C, right? So what is the change in the X coordinate as you move from 2 to 5? The total is 5. And when you're at C, you're already at 2. So the change is the total 5 minus this 2. So 0 to 5, from 0 to 5, you will remove 0 to 2. So it's good to see the subtraction done more in like a picture, like a visual story, right? So from the 5, you subtract the 2 and you get this gap of 3, right? The 3 represents how many changes, how many units you have to move along the x-axis to go from C to F. Obviously, you're not yet at F because we haven't done the Y movement yet, but at least now we've reached the X coordinate of F, right? So from 2, we've gone 2 to 3, 3 to 4, 4 to 5. We have changed the X by 3 and I've shown that as a total of 5 minus 2, right? So that is the change in X. The change in X as we go from C to F is 3. Same way, what is the change in Y? So for that, I have shown that on this side, because of which I've had to erase the scale information. The scale is the same as it has always been. So I've written that here as ditto. Now I'm just showing the movement along the Y. Obviously, just like along the X, when you're moving along the Y, you start from the origin, which is 0. The y value also starts from 0. What is the position, or what is the y value or the y coordinate of point C? The y coordinate of point C is 10. That means it's 10 units along the y axis above the origin, right? Whatever's here, I'm just showing it here so that it's not confusing, right? You're here. Then what you have to do to get to the y coordinate of F? The y coordinate of F is 25 from the start, 25 above the origin, right? That's what's actually here. I'm just again showing it here to be clean and clear, right? So that's where you have to get to, but you're getting to it from here. So how much do you have to move along the y-axis from the 10 mark to get to the 25 mark? Just like we did it over here, the total from 0 is 25. The total from 0 when you're at C is 10. You want the change. So you do 0 to 25. From that you remove, subtract the 0 to 10, and what you will be left with is just this much, which is 25 minus 10, 15. Check that, right? The 15 is what you get over here, and we've shown that here. So the change in the y coordinate, how much you move along the y to get to F from C, is this 15, right? The units, of course, is 3 seconds along the x-axis because x is measuring time, and 15 meter along the y-axis because the y-axis quantity is measuring distance, right? So the change in y is 15, the change in x is 3. We have now shown that here. This is where it gets interesting. Our abstraction now becomes possible, right? You know, we already know from our Frodo Baggins Lord of the Rings trip that B, C and F are definitely on the same straight line, which means what? The direction of travel from B to C is the same direction, same angle of travel from C to F. But this is where it gets interesting. The actual numbers of change in x and change in y, which we said determine the direction of travel. Direction of travel is determined by how much x changes and how much y changes. We saw that in the beginning, right? Those numbers are dramatically different for B and C and as to what they are for C and F. For B and C, the x changes by 1, the y changes by 5. But from C to F, as we've seen right now, the x changes by 3 and the y changes by 15. This is where it gets interesting. Even though the actual numbers of change in x and change in y are quite different from B to C as they are from C to F, somehow there is an evening out. There is a balancing out taking place. Even though x is changing by 3 as opposed to only by 1, from as you're going from C to F, is changing by 3. But accordingly, in the same way, the y, instead of changing only by 5, is now changing by 15. So what happens? How much ever you move, even though you're moving much more along the x-axis to go to F as you moved compared to how much you moved when you had to go to C from B. How much you moved here is much less than how much you have to move here. Even though you're moving more, same way, the amount you're moving up along the y-axis is also that much more compared to what it was earlier. So somehow there is a balancing out, there is an evening out taking place, with the result being that the direction of travel from B to C somehow balances out and is the same as what you have to do from C to F. So somehow this 1 and 5 and the 3 and the 15, they look different, right? 1 and 5 and 3 and 15. They look different, but somehow when you put them together, they are still producing the same direction of travel, the same angle, and therefore B, C and F are on the same straight line. Now what exactly is happening? Let's look at it closer. The question now is, what is common, right? The numbers themselves are different, right? 1 and 5 is different from 3 and 15. But what is that common underlying thread that is somehow common between 1 and 5 and 3 and 15, and which is therefore giving the same angle, which is giving the same direction of travel? Now, if you look at it, the answer actually jumps at you in the face, right? What is common between these two? The numbers may not be the same, but what is common between these two is, for every change in x by 1, y is changing by 5. I'll repeat. For every change in x by 1. Another way of saying change in x by 1 is unit change. 1 is unit. Unity, unit refers to 1, right? For unit change in x by 1, y is changing by 5. That is common. How is that the case? Over here, the first case is obviously very simple. B to C, x changes by 1, y changes by 5. C to F, x changes by 3. And how do we get the change in y? It's actually changing in the same way, because when x changes by 3, what does that mean? Changes by 1, changes by 1 more, changes by 1 more. That's what a change of 3 means, right? And for each of those changes in x by 1, y is changing by 5. That's how it's becoming 15. When x changes by 1, y changes by 5. X changes by 1 more, y changes by 5 more. When x changes by 1 more, y changes by 5 more. So by the time x changes by 3, 1 plus 1 plus 1, y has changed by 15. 5 plus 5 plus 5. So it's still changing in the same way as it's changing here. For every change in x by 1, y is changing by 5. The total change is different, because here the x changes by 3 and here it's only changing by 1. But how it's changing is the same. We're going to use a very important word which we'll elaborate on in great detail very soon. We use the word rate of change. Rate means what? Rate in English or in general mathematics means for every one. For every one, what is happening, right? For every unit, what is happening. The rate of change of y with respect to x, that means how much y is changing when x changes by 1, when x changes by unity. That is the same for C to F as it was from B to C. The numbers are different, 1 and 5, 3 and 15, but how the changes are happening, the rate of change is the same. And that is what causes this evening out and results in the same angle being produced, the same direction that you have to travel to go to C from B, and you have to continue in the same direction to go from C to F. Because while the numbers are different, the rate is the same. In both cases, what is the same is how much the y is changing for a change in x by 1. That is the common thing for both the cases, and that causes the various angles to even out and results in you having to move in the same direction, causing these points to be on the same straight line. So this is an amazing example of an abstraction, right? Because now we are no longer trapped by having to prove the entire thing by going literally point to point, 1, 5, 1, 5, 1, 5. Now we are no longer trapped by that 1, 5. Right? We can say the same thing. We are saying the same thing, but we can say it in a much bigger way. All we now say is that the reason any 2 points on this line are on the same straight line, what is common between them is not that from one point to the other, the x is changing by 1 and the y is changing by 5. It need not be. What is common is that regardless of where these points are, like B and C are here and C and F are there, what is common is not how much the x is changing and how much the y is changing, but the rate at which the y is changing with respect to the x. What is common in both cases is not the magnitude or how much x is changing and y is changing, but what is common in both cases is, in both cases, B and C and F, and you can extend that to any couple of points on this line, what is common is when x changes by 1, y changes by 5. So therefore, if x changes by 2, y changes by 10, right? 3, 15, 4, 20, and so on and so forth, right? So now that same earlier condition, which was very limiting, it was correct, but it was very limiting. It made us only have, it forced us to go from point to point. Now we are seeing the same condition in a broader sense. Instead of just seeing it as x changes by 1, y changes by 5, therefore same angle, therefore straight line. Now we say, pick any 2 points on the line. For every change in x by 1, y changes by 5. The actual values can be anything, but it's changing at this rate. This causes the angle to be the same, direction of travel. This makes the points fall on one straight line. So this is an example of a great abstraction. So now that we've seen the importance of what we now refer to as the rate of change of y with respect to x. And what does that mean? How much y changes for every change of x by 1, for every unit change of x as we go from one point to any other point on the straight line. That is the key. That being the same for any 2 points on that line, the rate of change being the same, that ensures that from one point to the other, the direction of travel is the same. And this is true for any set of points on this line. Same direction of travel obviously means all these points are on the same straight line. So now that we've got the importance of rate of change of y with respect to x, let's take a deep dive into this idea of rate and try to see what is the easiest way using simple mathematics to calculate this rate, right? So we'll take an example which is a little bit away from our main graph situation, or a day-to-day example that we can understand the concept of rate by, and then we'll come back to our graph. Now, if you think of normal mathematics, what are the 4 basic processes or operations we have in math? And essentially all math is a complex combination of all of this, right? We basically have 4 operations. We have addition, we have subtraction, multiplication, and division. Everything else is just a fancy combination of all of this, right? Now we are trying to look at this quantity rate, right? How much of one for every one of the other? How much of one quantity for every one of the other quantity, right? Now, out of these 4 basic operations, addition, subtraction, multiplication, and division, which operation will give us the correct way of calculating or computing this rate? Which of these 4 should we choose? For that, we'll take our simple day-to-day example. Now, I want you to imagine going to the supermarket again, a shop. And you go to the shop, see a bunch of things, and you see some pens. You want to buy some pens, and you ask the dude at in the shop, how much for those pens? And let's say he gives you some information like this. He says, hey man, the deal is very simple. 10 pens in this shop cost 100 rupees, right? So he's telling you that if you buy 10 pens, if you want to get 10 pens, you have to pay him 100 rupees. Now, you may not want 10 pens, right? You might want 30 pens, you might want 15 pens, you might want 500 pens, or you might want even 5 pens, right? So just because he's selling it in tens, you don't have to buy it in tens. So now what do? Supposing you want a different number of pens, supposing you want say 20 pens or 30 pens, right? What do? The simplest thing is, now you need to know how much money you want to pay. Now he's telling you that only 10 pens cost 100 rupees. Supposing you want, let's take a weird number. Let's say you want 35 pens, right? So how much money do you have to pay for 35 pens? So what calculation are you going to do? Now this information can be used, but it's a little tricky, right? The simplest thing that I have to do is, okay, if 10 pens cost 100 rupees, let me make life simple. Let me find out the cost of every 1 pen. Right? Once I know the cost of every 1 pen, that is if I know the cost of a single pen, then it's fine. Then no matter how many pens I have to buy, if I have to buy 10, multiply that number by 10. If I have to buy 15 or 20 or 35 like we said, multiply that cost that you found for 1 pen by the number of pens you want to buy, by 35. That many times, you will get the amount of money you have to pay, right? So our first step is find out the cost of 1 pen. Now, which of the 4 operations do we do when we want to find out the cost of 1 pen? Do we do addition, subtraction, multiplication, or division? Well, think about it. The 100 rupees is being shared across 10 pens, right? So 10 pens are like 10 people, right? 10 pens are sharing a total of 100 rupees. So if you assume that each one gets an equal share, how do you find the cost of 1 pen? You basically have to break up or split or divide this 100 rupees into 10 equal portions. That will give you the cost or the price of each pen. So the operation we're thinking of is not addition, not subtraction, not multiplication. We are thinking of division, breaking the 100 rupees across these 10 pens. That will tell you how much of money, how many rupees you have to give for 1 pen, right? And then we can calculate how much I need to pay if I have to buy 500 pens also. So the operation here is division. We do 100 rupees divided by 10 pens. The answer comes to 10 rupees for every 1 pen. We've written it like this. What that means in English is right here. Rupees 10 for 1 pen. A more mathematically correct way of saying that is rupees 10 per pen. The word per comes in. Whenever you see the word per, it basically means for every one, right? How many rupees for every one pen? Rupees 10 per pen. Now this begins to ring a bell, because that's exactly what we want when we say rate. How much of something for every one of something else. In this case, how many rupees for every one pen? How many rupees per pen? In this example, that is the rate for the pens. And therefore, if I have to calculate rate, now I know the process I have to follow is division. So now that we know that if I have to find out rate, that is how much of something is there for every one per unit of something else, the process or the mathematical operation I have to do is division. Now we will apply that to our example to find out how we can calculate the rate of change of y with respect to x as I move from one point to any other point in the line. What am I trying to find out? Rate of change. What does that mean? I want to find out as I go from one point to the other, how much is the y changing per unit change for every change in x by 1. Now we'll take inspiration from our pen example. If I want to find out rate of change of y with respect to x, basically what I want to do is I want to take the total change in y and divide that by the total change in x. Why? Remember our pen example, right? Basically what I want to find out, like our pen example, when I wanted to find out the cost of one pen, the rate, how much one pen was, what I did, I took the total amount of money paid, which was 100 rupees, divided by how much that money was paid for. It was paid for 10 pens. So the total amount of money divided by the total number of pens. When I do the division, I will get how much money per pen for every one pen. Same logic I am applying here. If I take the total change in y that happens when I go from one point to another point on this line, divide that by the total change, share it, split it by the total change in x that happens as I go from the first point to whichever the second point is. If I divide it just like this, what will I now get? How much is the change in y per change in x for every change in x by 1. Same logic as this. Basically, this is basically the meaning of division, right? Whether it's dividing total amount of money divided by pens or total change in y divided by total change in x, the meaning of division is actually the same. Whenever you divide two quantities, what are you actually doing? You are essentially finding out how much of the numerator is there for every one of the denominator. That is the basic meaning of division, right? Now, based on what units or what quantity is there in the numerator and the denominator, what it means in that particular situation is different. If the numerator is talking about total money and the denominator has total number of pens, when you divide, you will find how much money for every one pen. If the numerator has total change in y and the denominator has total change in x, when you divide them, again you're doing the same thing. You're finding out how much of the numerator is there for every one of the denominator. Here, since numerator is change and denominator also is change, now when you divide, you will get how much is the change in y for every unit, per unit change in x. Because whether it is this or whether it is this, the quantities may be different, but what you're doing is simply division. When you do division, it is how much of the numerator is there for one of the denominator. This is one example. This is one more example. That's all, right? So now when we do that here I have shown the actual substitution for our example, for our case, and I've chosen the same points that we've been dealing with. The first example I have chosen is the journey from point C to F, right? And we know that as we go from C to F, the total change in y, that is the y coordinate, it changes by 15 units, right? And since our unit for y is meter, it is 15 meter. So 15 meter here is not a y value, it's a change in y. Very important, right? And similarly, as I go from C to F, what is the change in the x coordinate? That also we've computed here. It's 3. The unit along the x-axis is second, so 3 seconds. 15 meter shared or divided by 3 seconds into 3 pieces. When you simplify it from here, this will give you this answer. 5 meter for every 1 second. Now, how do we write that in mathematics? 5 meter per second. The per in mathematics is written using the slash or the oblique. Why is the oblique required? Because this second, the unit second here, is actually in the denominator. The meter is in the numerator, right? Because in the numerator we have the distance quantity, and the denominator we have the time quantity. So when you divide distance by time, the time is actually still in the denominator, right? So the oblique shows you that meter is on top in the numerator and the second is in the denominator. So when I write it as 5 meter slash second, what we are reading it as 5 meter per second. 5 meter for every 1 second. This is now what we refer to as the rate of change of y with respect to x. The same calculation can also be shown for points B to C, right? In the case of points B to C, the change in x itself is only 1. So it's a very simple calculation, but we'll show it nonetheless. Right, you will get the same result. That's why I've shown this equal to sign here, equal to sign here, equal to sign here, because we're essentially doing the same calculation. Now here I've shown just B to C. The change as I go from B to C, the change in y is 5 meter, and as I go from B to C, the change in x is 1 second. 5 meter by 1 second, there's no major division to be done because anything by 1 is that number itself. Again, you get 5 meter per second read like this and written in mathematical form like this. So now we have taken the example. This you could repeat for any two random points on the line, and we'll do that very soon, and you'll see that when you repeat this calculation, you will get that for any 2 points on this line, the rate of change of y with respect to x is 5 meter per second. That being the same in its simplest form, it's 5 meter per second. That being the same causes all these points to be on the same straight line. So now we have understood very clearly that if I have to find rate of anything with respect to anything else, essentially what I have to do is division, and now we have done that for our example. So far, we've only been speaking about the 6 points that we actually plotted. Now we'll have to extend that discovery into the other points on this straight line, because apart from these 6 plotted points, there are a million other points, right? Random points which are not part of the 6 points that we plotted, right? So now this next part is very important. We're going to extend our discovery of rate of change being constant, and of course in the context of this line, that constant value of rate of change of y with respect to x is 5 meter per second. That rate of change concept, we will now extend it to other points on this line, random points in between the plotted points. So now we have 2 completely random points on the line, not plotted points, right? So I've taken one point here which is P, right? And that is in between the plotted point D and the plotted point E. P is somewhere completely random. And another completely random point Q, which is in between E and F. They're not exactly in between. I've purposely taken points which have no real symmetry. It's just completely random points, right? So P, if you can see, is a little closer to E than it is to D. And Q is similarly also closer to E than it is to F. The reason I've done this is very, very deliberate, so that once you figure out this analysis, then you can understand that it can be extended to any other point on the line. That there needs to be nothing special about that point, right? That's the whole idea. We're trying to develop ideas and conditions which will apply for all cases, right? Not just a few special cases. So now let's see how we can use what we already know about the plotted points and extend that to the non-plotted points. Again, a very important tool. We always go to the unknown using the known as leading steps, right? So now let's take them in groups. We're going to take 4 points, right? We're going to take B, C, P and Q. 2 plotted points and 2 random points. And we'll take them in steps. First, we will take the points B, C and only one of the random points P, right? And I've shown that over here, B, C and P. Now, obviously, by looking at the diagram, you know, just by seeing the diagram, that B, C and P are definitely on the same straight line. By looking at the diagram, you know. Now we know what that means, thanks to all our previous work. If B, C and P are on the same straight line, it means when I start from B and I travel in one direction, I go to C. and all I have to do is keep traveling in the same direction and I will hit P. And that is happening why? That is happening because as I go from B to C, maybe how much X is changing and how much Y is changing is different as what it would be when I go from C to P. But what is actually common, which is why they are on the same straight line, is that when I go from B to C, the rate of change of Y with respect to X is the same as what it would be when I go from C to P. That rate of change being the same causes the direction of travel or the angle to be the same, and therefore I travel in the same way to C and I continue in the same way to P, thereby causing B, C and P to be on the same straight line. So now we've written that over here. The rate of change, I've written it in short, rate. Rate of change for the journey from B to C is equal to the rate of change for the journey from C to P, because we know they are on the same straight line. And we know the values as well, right? So now we can find out the rate of change from C to P thanks to knowing what it is from B to C. Because from B to C we already know they are plotted points, right? And you can see from the graph or even from the table, the rate of change from B to C is what? What is the change in Y? Final value is 10, initial value is 5. 10 minus 5 is the change in Y, and the change in X is 2 minus 1. So 10 minus 5 divided by 2 minus 1. This rate of change, of course, it boils down to 5 divided by 1, which is 5 by 1, 5 meter per second. This has to be the same as what you would get if you did the same calculation from C to P, because they're all on the same straight line. Now we'll do the calculation for the points C and P. You can plot this on your graph and actually see what values you will get. You will get these particular values. Now I've chosen P such that the X value at P, the X coordinate as P, at P is 3.8. And when you actually plot it on the graph, you can actually check it. If you plot the graph correctly, you will see that if you choose a point P such that the X coordinate is 3.8, you will find that the Y coordinate will be exactly 19. You can check it in the graph and see that's what you will get. So now we've just taken that. If you fix the X coordinate at 3.8, you will find that the Y coordinate will be 19. And therefore now we can use that to find out what is the change in Y and the change in X as I go from C to P, right? So the change in Y will be 19 minus 10. You can see that from the diagram, 19 and 10. And the change in X, 3.8 minus 2, right? So if you want to find the rate of change, 19 minus 10 divided by 3.8 minus 2, that simplifies to 19 minus 10 is 9. 3.8 minus 2 is 1.8. So if you find the rate of change for the journey from C to P, it is 9 by 1.8, which in its simplest form again gives you 5 by 1, basically 5 meter per second. And this is exactly what we expected, and that's what we see when you actually take the points and plot them on the graph. That's what you will see, right? So we've used the known condition that the rate of change is 5 meter per second as we go from B to C, and we've extended that from C to P, because now what's special about extending it to the journey from C to P is for the first time now we have a point which is not being plotted. It's already a point on the line. It's an in-between point, right? So now we've gone from, B to C was plotted to plotted. Right? Using that, now we've got the understanding of what the rate of change is also going to be from plotted to unplotted or plotted to random, right? And that's where we are right now. One plotted point C to one non-plotted random point P. But because they're on the same straight line, the rate of change is the same. You can actually put it on the graph and see you will get the same value. So our condition is now being slowly extended to the other random unplotted points on the line. So remember what we are trying to do. What we are trying to do is use what we have discovered about the rates of change of Y with respect to X for the plotted points and slowly extend that and show how that same value of constant rate of change, in this particular example the value being 5, is also going to be the case for any two random unplotted points. We'll take the next group, right? First we started off with B, C and one unplotted point P. Now we will go to the next grouping. We will take the plotted point C, and now we will include the unplotted point Q as well. So now we're going to take C, P and Q. So one plotted point C and two random points P and Q. So you can see how we're slowly moving into the unknown into the dark side and shedding light on it, right? Now, if you look at the diagram, as usual, you know, if just by looking at the diagram, that the points C, P and Q are on the same straight line. And you know that if the 3 points are on the same straight line, what does that mean? That means, you can rest assured that it means that the rate of change of y with respect to x as you go from C to P will be the same as what it is when you go from P to Q. That's what we have shown here. Rate of change for the journey from C to P is equal to rate of change for the journey from P to Q. This is great because now for the first time in our problem, we have the two completely unknown points together. We're getting to where we need to go, right? And from the previous exercise, from the previous part that we did, you know that the rate of change from C to P, that is this, will be the same as what it was for the two plotted points B to C, because they were all on the same straight line that we just saw. So we're going to use that information as a bridge to come to this section. So we know that rate of change from C to P will be the same as what it was from B to C. We showed that calculation again here, 19 minus 10 divided by 3.8 minus 2, which is 9 by 1.8, which basically comes to 5 by 1. So we're going to use that. That has to now be the same as what I get when I do the same calculation from P to Q, right? And I've chosen Q, again it's completely random choice. I've chosen the point Q to be that point on the line whose x coordinate is 4.2. You can choose any number you want. I have just chosen 4.2. And you will find that when you take the x coordinate as 4.2, the point on the line whose x coordinate is 4.2, if you find out its y coordinate will come to 21. So just using the graph, you can do it as well and check. You can take any other point also you want, no problem, right? Take the point and now find out, do the actual calculation for the rate of change from P to Q. Change in y, 21 minus 19, divided by the change in x, 4.2 minus 3.8. In simple form, that is 2 divided by 4. These rates must be the same because they're on the same straight line. And when you do the calculation, you will see that that's exactly what you will get. 9 by 1.8 will become 5 by 1, which is 5 meter per second. 2 by 0.4 will also be in the simplest form, 5 divided by 1, which is 5 meter per second. And now, in a step-by-step way, starting from the plotted points, slowly involving one unplotted point and then finally moving into two completely random unplotted points, we have extended the condition and proved beyond a shadow of a doubt that if you have a straight line like this, you can take any two random points, because what we did for P and Q, you could have done for any other 2 points, right? You could do the same analysis for any 2 points. Now we've shown very clearly by going like a bridge one by one from plotted to unplotted that you can take any 2 unplotted points also, any 2 random points on the line. If they are on this same straight line, you can rest assured that the rate of change, the individual values of change in x and y could be anything based on where those points are. But what will be common is the rate of change of y with respect to x will be constant for any 2 points on this same straight line. And in this line, in the case of this line, that value is 5 meter per second. Whether you take B and C, whether you take C and P, whether you take P and Q, and now we're going to show very soon, we'll just take random points, some plotted, some unplotted, and we'll see what the values of change in y and change in x are, and we'll divide, and you will see that in all the cases, no matter what number is on the numerator and what number is on the denominator, when you do the division, the rate, fundamentally at the basic level, the rate will always remain the same, and for this line, it will come to 5 meter per second. Closing up this entire discussion, now that we know that for any 2 points on the same straight line, if they're on the same straight line, the rate of change of y with respect to x is the same. In this case, the value is 5. Now we can actually just take random points, okay? Some of them will be plotted points, some will be unplotted points on the line, random sets of points, pairs of points on the line, and we can actually show this is also something that you can do. If you've plotted the graph, you can take sets of points, right? wherever they are, doesn't matter, and you can actually find out the x and y values for all the points and calculate the change in y and change in x as you go from one point to the next, and find out the rate of change for each pair of points on the line, and you will see that the answers will all come to the same, and in this case they'll all come to 5. So we've just shown that over here, completely just random points. So the calculation that we're doing essentially is, as we go from one point to the other, we'll find out the change in y divided by the change in x, and that will give us the rate of change. How much is the change in y per unit or per one change in x, right? So I've also shown what journeys I have taken. You can take any journey that you want, any 2 points that you want. I've taken the journeys B to C, B to D, C to F, B to F, P to Q, just randomly, okay? And we can see what the changes are. So it's important to keep in mind, all the numbers that you see over here are not actual values of x and y. They are actually values of change in x and change in y as we go from these points. And if you want to remember what all this means in real life, when I go from B to C, I'm actually going from which point? B to C in the original experiment. So B to C is 1,5 to 2,10. I'm actually talking about when the car goes from this point to this point. So all these journeys that you are doing over here, they do have real life meaning. They are talking about journeys that the actual car is making from one point on the road to the other point on the road. So always remember, it all connects back to real life. Otherwise, sometimes we have a tendency to just get lost in the graph, right? And then that's where we get into a problem, because they were like, how does this connect to the real world? We're still talking about the moving car on the road. Nothing has changed. All right. So let's just do that quickly. I'm just looking at the changes now. You can actually look at the points on the graph and see if the change values do indeed pan out the way I've written them. When you go from B to C, y changes by 5 and x changes by 1. You can check that in the diagram. 5 divided by 1, the change ratio meaning division, right, is 5 meter per second. 5 by 1 is 5. Then when I go from B to D, the change in y is 10, the change in x is 2. So when you divide, the change in y per unit change in x still simplifies to 10 divided by 2, 5 for every change in x by 1, y changes by 5. Same thing happens when I go from C to F. The total change in y is 15. The total change in x is 3. 15 again broken into 3, divided into 3 steps. The answer is still 5 meter per second. So all of these are starting to show you that they all come back to 5 meter per second. Similarly, the journey B to F, change in y is 20 and the change in x is 4. 20 divided by 4, again in its simplest form, it's just 5 for every 1. 5 is a change in y for every change in x by 1. That's basically what's happening in all these cases, right? Even though the numbers look different. And the last case is also interesting. 2 completely random points, and these points are very close. So the change in x is not even 1. Right? At least in all these other cases, it was 1 and then 1 became 2, 2 became 3, etc. Now we've taken a case where the change is even less than 1. But the way it's happening, the rate at which it's happening is the same. I'll go into more detail on that very soon. That's why I've written the word potatoes. It might seem weird. It is, but it will become clearer just in a very short span of time from now. Now the last point, P and Q, the change in y is 2. We saw this in the previous section. And the change in x is 0.4, but when you do 2 divided by 0.4 in its simplest form, it's still changing at the rate of 5 meter for y for every second, for every unit change in x. So 2 divided by 0.4 is still 5 meter per second. Now, looking at these sets of numbers with a different perspective, looking at them in a more pure mathematical perspective in terms of giving it some mathematical terminology, we have this word in math that we refer to as fractions or a fraction. Simply put, a fraction is when you have one number on top divided by another number at the bottom. The number on the top we refer to as the numerator. The number in the bottom we refer to it as the denominator, right? So a numerator divided by a denominator. So if you look at all of these are all basically fractions. 5 by 1, 10 by 2, 15 by 3, 20 by 4, 2 divided by 0.4. Now, When you look at these fractions, if you actually look at the numbers that are involved in each of these fractions, the numbers are dramatically different, right? No two numerators are the same. 5 is not the same as 10. 10 is not the same as 15 or 20 or 2. The numerators are dramatically different. And similarly, if you look at all the denominators, they also are quite different. 1 is not the same as 2, 2 is not the same as 3 or 4 or 0.4, right? But what is common between all of these fractions? Even though the fractions themselves, if you look at them separately, they look quite different from each other, and they are. They are different from each other because the numbers are not the same. They are not perfectly identical fractions. But what is the same? What is common to all of them? When you actually do the division in each case, when you divide the numerator by the denominator and finish the division in each case, the answer that comes in its simplest form is the same, 5 meter per second, right? So even though the numbers themselves are different, when you divide and actually finish the division, the answer that you get is the same. So the result is the same, or the final meaning is the same. This is a very specific term that we give to fractions like this, which on the face of it are not exactly the same. They're not equal. In maths, when something is perfectly identical, we technically use the word equal. Now I have put the equal to sign. I'll come to that in just a bit. But technically speaking, these fractions are not equal, right? But in many ways, their final meaning is the same. So when things are not the same, but they are similar in the sense the effect is the same, the result is the same, even though they don't look on the face to be exactly the same, we use a more refined word. We use a word equivalent, right? So we say that these fractions are technically not equal fractions, they are equivalent fractions. Equivalent fractions means what? If you look at the fractions, they actually look different. It's not 5 by 1, 5 by 1, 5 by 1, 5 by 1, right? It's 5 by 1, 10 by 2, 15 by 3, 20 by 4, and so on. So they look different. But when you actually just look a little deeper, they all boil down to 5 meter per second, right? When you finish the division. So fractions which the meaning is the same, the result is the same, but they actually look individually quite different. These are called equivalent fractions. The reason we still use the equal to sign is the final mathematical value that comes after doing all of these divisions, 5 by 1, 10 by 2, it's the same. It's 5 in its simplest form. So these are what we refer to as equivalent fractions. I've also chosen one more very special important point. I've chosen this point R, right? Now R I have chosen to be exactly midway, exactly between the plotted point B and the plotted point C. So basically R's x coordinate I have chosen to be between 1 and 2, which is exactly 1.5. And when you find out for a point on the line whose x coordinate is 1.5, what its y coordinate will be, when you actually do it, you can do it yourself and see that the y coordinate will be also exactly between the y coordinate of B and C. That is exactly between 5 and 10. It will be 7.5. Now why have I chosen this point? And I'm going to do the same rate calculation using the point R, basically comparing the journey from B to C to the journey from B to halfway towards C, that is B to R. And the reason I'm doing that is to make one very, very important aspect clear, which is sometimes overlooked and it's a source of great confusion for students. So I've shown that summary over here, and that's why we're going to be soon talking about potatoes. Right? Now, if you take the journey from B to C, again you can check all this from the diagram. When I go from B to C, the change in Y obviously is 5. And the change in x is 1. So if I want to find the rate of change, 5 divided by 1, it's 5 meter per second, changing of y by 5 per unit change in x. Now, obviously I must get the same answer when I do the journey from B to R, right? Because B, R and C are all on the same straight line. So I should get the same result when I do the journey from B to R, which is what we have shown here. When I go from B to R, you can again check in the diagram, the x coordinate or the x value changes by 0.5 from 1 to 1.5, changes by 0.5, and the change in y is from 5 to 7.5. As we go from B to R, the y changes from 5 to 7.5. So the change in y is actually 7.5 minus 5, which is 2.5. So again, when you want to find out for the journey from B to R, what is the rate of change, right? How much is the y changing per unit change in x? You do the same thing, 2.5 divided by 0.5, which will give you the answer 5 meter per second. Now, this is very important to understand because this is sometimes where some students can get tripped up, and it's understandable to see why. When we have been always saying so far that the rate of change of y with respect to x is 5 for y for every change in x by 1. That was fine as long as we were doing bigger numbers, right? So when I said, okay, when x changes by 1, y changes by 5. Then when 1 becomes 2, the change in y becomes 10. 2 becomes 3, it becomes 15. 3 becomes 4, it becomes 20. So that's all fine because when you want to look at 4, you think of it as, when you think of the number 4, it's basically 1 plus 1 plus 1 plus 1, right? So for each of the 1, you do 5 plus 5 plus 5 plus 5 and you get your 20. The problem happens when you get a change in x which is not yet 1. In this case, we've already done that case here. I want to take an easier version of that here. The same thing can be applied to this case as well, the points P to Q. Wherein here, when I go from B to R, the change in x is not yet 1. It's only half of 1. It's not 1. The change is not from 1 to 2. I've stopped at 1.5. So the change in x is only 0.5. It's only half of 1. So then the question naturally comes to a student, right? Wait a minute. I know how to calculate changes in y for larger changes in x because the simplest form I got, I know that when x changes by 1, y changes by 5. So any number bigger than 1, I just have to accordingly add or multiply and I will get the change in y. The problem that comes now is, now I don't even have a change in x by 1. The x has changed only by 0.5 and stopped. How do I use this rate information? My rate information is what? Y changes by 5 per unit change in x. That is per change in x by 1. So how do I now find out how much y will change when x changes by less than 1, right? How does this rate going to be of use to me? That's a very important question. And now when we look at this example, we can get some clarity as to what exactly is happening. See, just because you decided not to change the x by one whole unit, you changed only half, you went halfway and stopped. It doesn't mean the way in which y is changing as x changes or the rate has to change, right? That rate, the way the y is changing as x is changing is still the same, right? It's just that you haven't done the whole journey of changing x by one whole unit. You've only changed halfway and stopped, right? So obviously, if y is changing in the same way as with x as it was always doing from any point, if you change by half the amount, the change in y also will be half, right? So what basically happens is when you change x by 0.5 is what we do here from B to R, you're changing x by only half the amount. Because you're changing x by only half the amount, half of 1, what will happen to the change in y? The change in y will also be half what it would have been if you had changed by 1. If you had changed by 1, the change in y is 5. Now you changed by half of 1, the change in y will be half of 5. It will be 2.5. You will get 2.5 and 0.5. So it's not that suddenly the rate of change is different. The rate of change is the same, right? It's just that you have not changed all the way up till 1. You have stopped at 0.5. So the y change also will stop at 2.5. If you continue the process and you change from 1.5 to 2 and you reach the point C, basically, you change by another 0.5, then the y will also change by another 2.5 and then you will have 0.5 plus 0.5, total change in x is 1, and for the y, 2.5 plus 2.5, the total change will be 5. You will get back your change in y by 5 for a change in x by 1, right? So the rate is the same. It's just that you have chosen to stop halfway. So even the y change also will stop halfway. So it's very important to understand that even though the change in x is 0.5, right? The rate at which y is changing with respect to x is still 5 meter per second. Change in y by 5 for every unit change in x. For every change in x by 1. Because that rate is the same, because that is not changing, when you change by less than 1, by half of 1, accordingly, to adjust it perfectly, the y will also change by half of what it would have changed if you had changed by the full 1. If you change by the full 1 and it changes by 5, now you change by half of 1, you change by 0.5, it will also change by half of 5, 2.5. But the way it's changing is the same, the rate is the same. That's very important to understand. To make this even clearer, if this is still a bit confusing, this is where our potatoes come in. It is very equivalent or very similar, same result as what happens when you go to a shop to buy potatoes. Now you could do this for the same story you can say for pens also, but earlier we did pens, we use some different numbers for pens. I'm also feeling a little hungry right now, so I'm going to use potatoes. It doesn't matter what item you're buying in the shop, it's the same thing. Supposing you go to the shop, right, the grocery store, and you want to buy potatoes. And the shopkeeper tells you, ask the shopkeeper, what is the rate of the potatoes? Which basically means you're asking him for one potato, how many rupees to pay, right? So what the shopkeeper tells you is, one potato costs 5 rupees, right? So the rate is 5 rupees per potato, 5 rupees for one potato. But now let's say you are a weird guy like me and you don't want one potato. You want only half a potato, right? So what amount of money do I need to pay if I want half potato, but if the rate has not changed? The rate is still 5 rupees per potato. It's just that I don't want a full potato, I want only half. So accordingly, while keeping the rate the same, what should be the smaller amount of money I need to pay? I am requesting for half of one potato. Right? And therefore, what must be the amount I need to pay? Half of what I would pay if I had actually bought one full potato. So if I want 0.5 potatoes, that is half a potato, I will now pay half of 5. I will pay 2.5 rupees. And if you finish that process to show that the rate is still the same, it's going in the same way, right? If I finish the process, if I now ask for the other half potato, for that other half I again pay 2.5 rupees. So by the time I have one full potato, I have still paid 5 rupees. So the way the price is changing based on the amount of potato I'm buying is still the same. It's changing at the rate of 5 rupees for every potato, right? Just because you buy half a potato, the rate is still the same. It's just that you have not bought one full potato, so you will pay half of 5. You will pay 2.5, right? So just because the numbers are less than 1, it doesn't mean the rate is different. This is a very, very important idea that becomes very crucial when we do later advanced mathematics like differential calculus, integral calculus. It's a very simple idea, but sometimes can cause some confusion. It's confused me a lot and it's taken me a lot of time to figure it out. So I just thought I'll lay out that whole thing very clearly. Now it's time to just take a quick recap and to see where we are in this long journey of exploration, because we've done quite a bit. So let's just see where we are, where we started off from and where we need to go. So at the beginning of this lesson, remember we asked ourselves 2 important questions and we've answered the first question, and that was, when we take 6 original plotted points and actually plot them, why do they perfectly line up in one straight line? We saw why that happens, and we were also able to do what is called as an abstraction, and we found out a larger, more expanded condition for what happens when you have points on a straight line. And we saw that if you have a straight line, you can completely rest assured that for any 2 points on that straight line, or for all sets of points on that straight line, as long as they're on that line, what that means is that the rate of change of y with respect to x as you go from one point on that line to any other point on that line, that value will be the same. And in the case of our line, in the case of this line or this graph, that rate of change was 5 meter per second. We've answered the first question. Now, what was the second question that we had? The second question was, okay, once you plotted the 6 original points, then we said, don't worry, using Hansel and Gretel, you can confidently just see the shape that they are forming and join the straight line, draw the straight line through the 6 points, and that line will be the graph of the equation y equal to 5x, and therefore the graph of the original experiment, which means we said you don't have to actually plot every single point in the original experiment. If you actually did that one by one and you actually plotted every single stage using the equation and the table on the graph, the shape that you would get would be this line. So you don't have to do it, just use Hansel and Gretel, use these points as breadcrumbs, and you can completely be sure that this straight line is what you would get as the graph of this equation and therefore the experiment. And after that, we threw ourselves a curveball, right? We said, well, can you answer that question in a deeper way, not just using Hansel and Gretel, as to how can you be so sure? How can you be so sure that if I actually plotted every single stage one by one, this was the exact shape that I would get? And we threw ourselves a curveball by saying, how do you know? Maybe when I actually did the plot, I would have gotten that weird snake-like pattern or some other shape, some dragon or something else, who knows, right? How can you be perfectly sure? So now we can answer that question in a more mathematical way, in a deeper way than Hansel and Gretel, that yes, once you get the 6 points, you can confidently join them with the same straight line, and that line will actually have all the other stages in the experiment. It will all be there only on that line. It will not be anywhere else. Now we can answer that question thanks to all that we've already discovered. In order to answer this question, we'll just have to rephrase it, right? Just look at the same question in a different way, from a different angle, so that when we look at it in that way, we now have a way to start working on it. Sometimes when you look at a question like this, you know what question you want to answer, but the form that the question is in, it doesn't help you take the first step, right? So we want to answer the same question. We want to prove that this line is the graph of the equation and therefore of the experiment. But in order to do that, we look at that question in a different way, in a way that helps us actually make the first step. It tells us what we need to do in order to prove this, right? So let's do that right now. Very simply put, all we can say is that if this straight line is indeed the graph of this equation and therefore of this experiment, what does that mean? What must be true? That means that if I had actually taken every single stage in the experiment and physically plotted it, that means not just these 6 points, if I had taken every single x value, those infinite x values, right? Take every single x value, put it in this equation, find out y by doing y equal to 5x, get the ordered pair on the table, take that point, go to the graph here, go to the Cartesian plane here, go x units along the x-axis and 5x along the y-axis. X, 5x, x, 5x. Do that for every single stage and then get all the points and then see what shape the points are forming, right? And then join them and get that final shape, right? Now all we're saying is, if when you did that, if that final shape that you got was indeed this straight line, if the straight line was that final shape that you got after doing every single plot and joining the points, if the straight line was that shape, then what must be true? What must be true is that you can take any point on this straight line, and what must be true is that for any point on this straight line, the point's y coordinate must be 5 times the point's x coordinate, because that's how it would have come, right? That's how it came. For every point, what did we do? Because it comes from this experiment and therefore from this equation, how did we plot it? We went x along the x-axis, 5x along the y-axis, x, 5x, x, 5x. Got all the points? And we would have joined them, right? So now if you join them and if the shape that you get was this straight line, obviously what does it mean? It means, just looking at the same thing in reverse, that every single point on this line has to have its y coordinate as 5x, its y coordinate as 5 times its x coordinate. That's what I have shown over here. On this straight line, I have taken a completely random point. I have taken this point n, right? So I've just placed it here. You can repeat this study by placing this point wherever you want on the line. There's nothing special about this location. It's completely random, right? Now this particular point N has some value of x coordinate here, x, distance from the origin along the x-axis, that is x, and it has some y coordinate here, distance along the y-axis from the origin. So this point N has the coordinates x, y, right? So all I have to now show is that if this line is indeed the graph that I would get if I plotted every single point on this experiment on the plane, if this line was that graph, then you can take any point on this line like N, and all I have to now show is that for any point on this line like this point N, its y coordinate will be 5 times its x coordinate. If I can show that for any and every point on this line, the y coordinate is 5 times the x coordinate, then I can prove beyond a shadow of a doubt that this line is the graph of this equation and therefore of this experiment. So now we have rephrased the question. All we're going to do now is take this point N and try to basically prove that no matter where this point is, as long as it's on this straight line, its y coordinate will be 5 times its x coordinate, and therefore, in other words, y equal to 5x is true for all points on this line. Now we have something to work towards. So how do we go about doing this now? This is where our rate of change condition comes in very handy. So now as you can see over here, again I have chosen 3 specific points on this line. Of course, one of them is our completely random point N, whose coordinates are x, y, and the other 2 points I've chosen. For the first time now, I have chosen the origin itself, the very first point, the starting point of this entire experiment, A 0, 0, and you can see very soon why choosing this point in these kind of explorations becomes a game changer. 0 can do a lot of fantastic things, right? So A 0, 0, and I've again gone with B 1, 5. You can choose any other point you want. That's completely up to you. So the 3 points are A, B, and N, right? Now, when you look at this diagram, as always, if you see A, B, and N, they are all on the same straight line, which therefore means, thanks to our rate of change condition, you can go from A to B, you can also do the journey from B to N, and you can also do the journey from A to N. What will be common to all these 3 journeys? Because these points are on the same straight line, same direction. That means what? What's common to each of these 3 journeys is that when you do these journeys, the rate of change of y with respect to x will always be the same, even if the actual numbers of how much x and y changes will be different. Let's see that over here. So rate of change of y with respect to x, too much space and too much to write. So I've just written as rate from A to B is equal to rate from B to N, which is equal to the rate from A to N, and we know that in the case of our line, that value is 5 meter per second. Let's put that in more mathematical form. You can actually see how the changes have been calculated from the diagram. I have just shown it anyway. When I go from A to B, the change in y, how do I get the change in y? The final y minus the initial y, that is the y of B minus the y of A, which is actually 5 minus 0, divided by similarly the change in x, x of B minus the x of A, final minus initial. That gives us the change, right? So divided by 1 minus 0, which is basically 5 by 1. Doing the same thing for the journey from B to N. If you see the diagram, it becomes very clear. When I go from B to N, the change in y is the final value of y, which is the y coordinate of N. From that, you take away the y coordinate of B. So that is what? Y, from y, you remove 5. So y minus 5 divided by, similarly, the change in x, which is final x, that is that of N, minus the x of B, which is x minus 1, because we don't know the x and y values for N. So we just call it x and y, right? Because they are unknowns. So then we have x minus 1. So the ratio will now be y minus 5 divided by x minus 1. And likewise, for the last journey, the journey from a to n, again the change in y is final y minus initial y minus 0, right? And divided by the change in x, final x again minus the initial x, divided by x minus 0. So now you can slowly start to see the benefits of using origin, right? When you use origin, what happens is, like you can see over here, the change in y, because one of the terms is 0, we'll look at this in more detail later as well. The change in y actually becomes the y value itself. Here the change in y is y minus 0, but y minus 0 is just y, right? So here actually the change in y is actually the y coordinate of n itself. And similarly, the change in x is actually the x coordinate of n itself, because the other term is right at the start. The other term is 0, nothing, right? So again, all of these fractions or all of these ratios is a fancy word for division of fractions, they are all equal to 5 in this case. So now we have this big equality, this equal to this, equal to this, equal to this. And to prove what we want to prove, we are now going to focus our attention on this equality. Y minus 0 divided by x minus 0 is equal to 5. Now you can slowly see the result that we want is beginning to take shape. Completing the last part of the proof, so we have y minus 0 divided by x minus 0 equal to 5. Of course, y minus 0 is just y really, and x minus 0 of course is just x. So this actually simplifies into y divided by x is equal to 5. This is quite an interesting result, because till now, so far, what we saw when we were dealing with changes in x and changes in y, we always saw that for this line, the change in y divided by the change in x was always equal to 5, right? That's true for any 2 points on this line. Now we realize that is also true, but something beyond that is also true. That is, for any point on this line, not only is the change in y by change in x equal to 5, but the actual value of y coordinate of a particular point on the line divided by the value of that point's x coordinate is also equal to 5. So y by x is also equal to 5 for any point on this line, because as we saw, there's nothing special about this point n, right? I could have done the same process by placing this point n anywhere else on the line, and the entire proof would be exactly the same. So now we realize that for any point on this line, the value of its y coordinate divided by the value of its x coordinate, y by x, is equal to 5. So we were able to make the transition from change in y to change in x to the actual value of y divided by the value of x, because we made one of the points in our journey the origin, the very start, 0, 0. That's the beauty of including the origin. So now we have y divided by x is equal to 5. And rearranging that, we see that what is true for every single point on this line is that y is equal to 5x. That means its y coordinate is equal to 5 times its x coordinate, and this is exactly what we wanted, right? Because now this is true for every single point on the line, we can completely be sure that every single point on this line actually matches every single stage on this experiment. And that means if I had actually plotted every single stage individually and looked at the shape that I would have gotten is exactly this line, and therefore I don't have to do it. Hansel and Gretel were right. Now I know why they were right, and therefore now we have completely proved after so many hours that this line, the straight line, and not just the 6 plotted points, the full straight line is the graph of this equation, and therefore is the graph of this experiment. So now that we've proved what we need to prove, it's also important to take some time and do a little bit of thinking back, looking back as to what worked and why it worked, what we refer to as sort of reflection, right? And this is very important because whenever we have methods that work, right, we always have to be alert and be clever enough to realize that this method need not only work in this case, right? We have to take the basic idea of why this method worked, how this method worked, so that tomorrow when we are in other situations which are similar to this, we can apply the basic method in those situations and obtain the results that we want in those situations as well. So looking back at whatever worked and trying to from there figure out what the larger method was, it's another kind of abstraction in a way, right? I'm not interested in the individual numbers of this experiment. I just want to see, okay, why did it work? Whatever I tried, why did it work? What was essentially the reason behind which this method worked, so that I can now ignore all the individual measurements that are true to this experiment, take the method, right? Abstraction, a bigger view, take the method and then use that method in other areas as well, something which is absolutely critical, right, in physics and chem and bio and higher mathematics, and basically critical in helping us seek truth as to how all of this existence is working, right? So let's look at that over here. Now here we're looking back at how we use the origin, especially the 0, 0 with such great effect, right? So if you look at what I have shown here, I have basically shown that same rate of change calculation as to how it panned out between, comparing the cases of when I went from B to N versus what happened when I went from A to N, that is the origin to N. And we'll just look at how the changes in X and the changes in Y panned out, right? So when we went from B to N, right, let's look at the journey from B to N just in terms of first the change in the X coordinate, that is the change in the X position. See, we can show that from the diagram as well, and I've written it over here as well. When you're going from B to N, what is the change in the X value, in the X coordinate? So how do we do that? Remember, all the X values, that is positions along the X axis, are measured from where? They are measured from the starting X value, which is 0, which is referred to as the starting point or the reference. Everything is measured from there, right? So for example, when you are at point B, in terms of in the X direction, you are 1 unit away from the start. So I have shown that here. From 0, you are 1 unit away, right? And from here, if you have to move to the X coordinate of the point N, the X coordinate of the point N is X. What does X actually mean? X means it is X units away from the start. Just like for B, it was 1 unit away from the start. So the 1 for B and the X for N only have meaning when you see them as from the start, or in other words, I use the word relative to, right? On its own, 1 and X don't have any meaning, right? Any measurement like this only has meaning as to where it is from where you started making the measurements. What did you take as the starting point, right? So 0 to X is the total for the point N, right? And 0 to 1 is the total for point B, right? So if you want to see the change in X as you go from point B to point N, you're looking at this interval, this gap, right? Which is the total for point N, which is 0 to X. From the 0 to X, you remove what you already did. You were already at B, right? You didn't start from the origin. You are already at B. You want to know how much more you have to move from B to get to the X coordinate of N, right? So since you are already here, how much more you have to move, or the change in X is the total X, which is from 0 to X, that is for the point N. From that, you remove the journey from 0 to the X coordinate of point B. That is, you remove 0 to 1. So from 0 to X, we remove 0 to 1, right? And then we are left with this much, which is the change as I go from the X coordinate of B, which is 1, to the X coordinate of the point N, which is X, because I don't know what it is. So I've shown that over here, right? The change in X, 0 to X, from that you remove 0 to 1. Right? In other words, what you're doing, 0 to X, the value is just X, right? And 0 to 1, of course, the value is 1, right? So you're doing X minus 1. Another way of thinking about it is, see, when you move from B to N, your initial position is B. You're starting from the x coordinate of b, right? 1. And what is your final position? Your final position is you're here, you're x units away from the start, you're at the x coordinate of the point n, right? So the final value is x, the initial value is 1. So when you want to find the change, you're doing what is the final? From the final, take away the initial, and that will give you the change. From the final, take away the initial, that will give you the change. So whenever you're doing change in something, you're usually going to be doing what is the final value of that something minus what was the starting value of that something, that will give you the change. So x minus 1, which is final minus initial. The exact same thing we can apply to the change in y as you go from b to n. As you go from b to n, I've shown the changes in y here. When you are at b, you are 5 units away from the start in the y direction. The start again is 0 in the y direction. This time you're 5 units away, you're here, right? What is the change as you go from here to the y coordinate of point n? And the y coordinate of point n is just y units away from the start, because I don't know what the value of y is. N is a random point, right? So finally you are at y, that is finally you are y units away from the start. Initially you are 5 units away from the start in the y direction. So what is the change? The change is final, which is 0 to y, minus you remove the first part of the journey that you already did, that is you remove the head start, you remove 0 to 5, you remove this, and that will give you this. That's what we've shown over here. Change in y, 0 to y total or final, minus 0 to 5, that is where you were in the beginning, because you didn't start from here, you started from 5, right? So minus where you were in the beginning, that is y minus 5, again final minus initial. So this is basically what happens for the changes in x and y when I do the journey b to n, right? How does that get very simplified when I do the journey from a to n? Everything remains the same. It's the same process. You're still finding changes in position, right? The beauty is that when you change, for example, when you're doing the change in x from a to n, now you are starting itself at the origin. You're starting at the 0 position for both x and for y. You have not already moved. Right? In the previous case, we already moved to B. Then we are only finding out how much more to move to get to N, whether it's in the X direction or in the Y direction. Here, when you go from A to N, you haven't already done some cheating. There's no head start. You're starting right at the beginning, right where everything began, the origin, right? So there's no head start, as we say, right? So over here, we see that over here, the change in X is 0 to x, that is the final position, minus the initial position. The initial position is no real position. You haven't moved away at all. You're at the start itself, right? So 0 to x minus 0, nothing to remove actually, right? So x minus 0, it's still the same calculation, final minus initial. It's just that the initial is 0 here because you haven't moved, right? Which is basically x. And the same thing happens to y, right? The change in y is the final value of y. How much further away from the origin are you along the y-axis when you reach point n, which is y, minus where were you in the beginning? You had not moved at all in the beginning. You were at the origin itself, right? So 0 to y minus 0, which is y minus 0, which is y itself. So the difference between these two cases is important. In both cases, the calculation you're doing is the same, right? You're trying to find out the change as you move from one location to the other. The key difference here is, in this position, when you were trying to find out the change, your initial position itself was you had already moved some distance from the start, whether it was along the x-axis or along the y-axis. You had already moved some initial distance and you only wanted to find out how much more to move to get to the final position. That was not the case here. Here, you hadn't done any initial movement. Initially, you were at the start itself. So something really interesting happens here. When you find out changes in position, wherever your initial position is the start itself, is a 0 mark itself, then what happens? How much ever you change the position, that will be your final value also. That will be your final position from the start. If I'm starting from 0 and I change my position by x, So my change is also x, and my final value is also where? Where will I be? I will be x away from the start, because I hadn't already started. There was no head start, right? So not only is my change x, my final value is also x, right? Similarly here, when I'm going along the y, since I'm starting from 0, when I change my position by y, my final position value also becomes y. That's not the case over here, right? Here we only changed by this much. When I went from b to n, I only changed by this much, but my final position was x, but the change was only x minus 1. Similarly here, I started from 5 and went to y. My final position was I was y away from the start, but my change from b to n, when I moved, my change was only y minus 5, right? But when you start from 0, the change in your position and the final value of your position from the start, they are one and the same, because you are starting from the start. You haven't already moved before you start doing the experiment, right? You're starting right from the beginning. So this is the key difference, and this is what helps us get to the proof very easily. So therefore we can see, when I do the rate of change calculation from b to n, I get y minus 5, change in y, divided by x minus 1, that is change in x, equal to 5. But this is not of very great use for me to prove why that this entire straight line will be the graph of this equation. That I can do when I choose a to n, because when I go from a to n, the change in x is also the final value of x. The change in y is also the final value of y from the start, right? So y minus 0 divided by x minus 0 is equal to 5. It's the same rate of change calculation. It's just that the initial values are 0, 0, right? That simplifies to the actual value of y divided by the actual value of x equal to 5. That gives me y equal to 5x. So this is a very, very important, again, an abstraction to help us understand why it is important to understand the difference between the actual value of a particular quantity, that is what the value is from the start, and differentiate that, understand the difference between that and how much the quantity is changing by when it goes from one value to another. So therefore it gives us the need to have two separate mathematical symbols. Two separate mathematical symbols, one symbol to show what the value of a particular quantity is, right? And another symbol to show what the change in the value of that particular quantity is. These two are two different things in many situations. We will see that right now and go into the formal notation, which is absolutely crucial. Once you understand this notation, that is when, again, more advanced abstract mathematical ideas, etc., become very easy, because these are again tools that you're now completely familiar with. Now we have seen the need. First thing is always to see the need for any kind of new symbol, any kind of new notation, right? Now if you see this entire experiment and really think, you're like, yeah, there is a difference between how much a quantity changes and what its final value is, right? So we need one symbol to show us the change in the quantity, that is the calculation that I do, final minus initial, and another symbol to show us, okay, after that change, what is the final value of that quantity from the start, right? So two separate symbols are needed. That's what we look at right now. So now we can look at how to develop the proper notation to differentiate between the change in a quantity versus a symbol for the actual value of the quantity at any stage in the experiment. So for this, we're taking a simpler journey. I'm taking 2 points whose coordinates I completely know. I want to deal with more numbers at this stage as opposed to letters and variables, right? So let's take a very simple case. We're taking the journey from the point B, which is 1, 5, and we're going to the point F. The point F, which is 5, 25, that can also be seen on the table here. And we're going to do the same thing. We're going to do in 2 steps, right? That's the advantage of having Cartesian coordinates. We can first move along the x-axis and see what the change in x is as I go from B to F while not moving along the y. And then I can keep my x position the same and then move along the y and see what the change is as I go from B to F. The beauty of perpendicular Cartesian movements, right? So let's just look at the journey as I go from B to F, only looking at how the x coordinate has to change. So let's look at that here. So we're looking at the change in the x position, the x coordinate as I go from B to F. That diagram we have shown here. Right. So when you imagine, it's almost, you think of it like an actual journey. Think of it as you are there on the x-axis running, right? So imagine you were initially at B, right? So this is you or me or whoever, right? This is you on B, right? And remember, because you're on B, you're not starting at the origin. You're not starting at the value x equal to 0. You have already moved, right? You have what we call as a head start. You are starting from point B. When you're at point B, your position is along the x-axis. You are already 1 unit away from the origin. You have already moved from the start by 1 unit. Therefore, your original x value, we will now call it x1, the first value of x, that is the x coordinate of B, which is x1, which is 1. That is your starting position. Your starting position is not x equal to 0. Your starting position is x equal to 1. We will call that x1, the starting position. Now from here, what do? You start to run or you start to walk, and this is the journey that you take. And where do you finally stop? You finally stop when you reach the x coordinate of point F, right? I'll repeat, the x coordinate, that is the x position for the point F. And that is, as you can see from the graph, that is when x equal to 5. So you keep walking and you reach F. When you reach F, what is special about F? The x value. When I say x value, that means at F, what is the distance or what is the position? Again, from where? From the start. From x equal to 0, what is the total position when you reach F? When you reach F, you reach an x value of 5. What does this 5 mean? This 5 means 5 away from the original start, 5 away from the 0. That's what 5 actually means, right? So you started from 1 and you've moved to 5, but you're now 5 away from the 0. That's what 5 actually means. We will call that your final position, your final value of x, which is now called x2. In other words, x2 is the x coordinate of point F. x1 is the x coordinate of point B. So you have moved from x1, which was 1. You have moved, and you've reached x2, which was 5, and that is 5 away from the start. So now I want to find out only this distance, right? This journey. What has been the change in my x position or in my x value as I have gone from B to F? So I only want to find this, right? This distance, this change. How do I do that? From the diagram itself, it's clear, right? You take the final position, that is the final value of x. The final value of x is, again, all the measurements are from 0, right? The final value is 0 to 5, which is x2, this total, right? But you didn't start from 0. You started from B. You already had a head start. That is, you started from the x1, whose value was 1. So you started only from here. So how much is the change that you made? You didn't make a full change of 5. You only made a change of this much, right? Which was the total, that is 5 minus, from this 5, you remove the head start. You remove what you already did, right? Where you started from. You remove the 1. So you're going to remove from the x2, you're going to remove the x1. This is 0 to x2, the total. From that, you will remove your starting position because you didn't start from the beginning. You started from x1. You will remove x1, and this will be the change, which therefore means x2 minus x1. This is what we are showing you here, right? Change in x, final x from the start is 0, minus initial x from the start, that is initially where you were, again from 0. Initially you were not at 0, you were at 1, right? So 5 minus 1. Therefore the change is x2 minus x1 equal to 5 minus 1, which is 4. The change is only 4, right? This is why we need a separate notation, right? And that notation we have shown you here. We write it like this: triangle, it's a nice small triangle, triangle x, okay? Triangle x is showing us the change in x. What is that? x2 minus x1, final minus the head start, minus the initial, 5 minus 1, which is equal to 4, right? And therefore now you can see the need for different symbols, right? Because in this small experiment you see your starting value of x, that is x1, was 1. Final value of x, x2, was 5. But what was the change? You went from 1 to 5. You didn't go from 0 to 5. You started at 1 and you went 2, 3, 4, 5. So your change was only 4. That's why we need a separate notation, because the values are different, right? The change is this triangle x equal to 4, right? When you see this triangle x, in your head you think change in x. And now we have a specific word for this triangle. This triangle is actually the Greek letter delta, right? And it's now used in modern mathematics to show change in any quantity. So when you see triangle x, you will read it as delta x. This notation is very, very important, because all advanced mathematics, whether it's trigonometry calculations, calculus, statistics, all of this stuff, we're talking all the time in terms of how one quantity changes when another quantity also changes, how we compare changes, right? So changes are very, very important in quantities, and in not just in mathematics, in all kind of sciences, right? So most of it will be filled with this. You got to become good friends with this symbol delta, right? Delta x. So when you see the triangle x, you say delta x, and in your head you are thinking change in x. And now you can see why we need the separate notation, right? Because the actual values of x, right, are x1, which was 1. The final value is x2, which was 5. But the change delta x is 4, right? 1, 5 and 4 are quite different from each other, right? So one is the initial value of x, final value of x, and the change is the final value minus the initial value. That is the change, and that is notated by the symbol delta x. So this gives us a very, very important tool to make sense of higher mathematics. The same thing, the same notation can also be shown for the movement along the y-axis as you locate f from B. Now I'm not going to go do the whole thing step by step again. You can run through it. It's exactly the same application as what we did for x. And again, you can see the advantage of having Cartesian coordinates, right? Because when you are moving along the y-axis to go from B to f, you are only moving in this direction, so you are not changing the x coordinate of either B or of f. So you can do it separately, and that's what we have shown over here. I've just shown just the y-axis or the y direction, right? And everything else pretty much remains the same. So just to do a quick summary, remember all the actual values of y, whether it is for B or whether it is for f, etc., they are all measured from the starting value of y, which is 0. But in this case, what's happening is you're not starting your journey at 0, you're already starting your journey at B. And what does B mean? B, the y coordinate of B, I have shown using the subscript 1, right? So y1, right? And that y value is what? When you are at B, your distance along the y-axis from the start, from where everything is measured, is 5 units, right? You're already 5 units from the start when you're at B. So we call that y1, that is the y coordinate of B. And from here you start moving, you walk, and you reach the y coordinate of f, and that value is 25. What does 25 mean? It is 25 from the start, right? 25 actually only has meaning as 25 units from the start of everything, that is from y equal to 0, right? So that is the value 25, but that is not how much you have moved, right? Because you already had a head start. You didn't start your journey from 0. You already moved 5 units to B, and you're starting your journey from here, right? So even though your final position is 25 units along the y-axis from the start, that is not your change in position, because your initial position was 5 units from the start, from the 0 mark. So your change is only the total of 25 minus the 5 that you already did, right? So your journey is only this much, which therefore we say as final minus initial, y2 minus y1. We use the subscript 2 just to indicate point F. If you have more points, you can use other subscripts y3, y4, y5, etc. y5. y5, not Wi-Fi. Okay, so bad jokes. Okay, so that's basically it. That's what we have shown over here, right? And therefore, when you finally find out the change in y, you have to use the new symbol that we have, delta y, and you can see the use of it here as well. The actual values of y, y1 is 5, y2 is 25. But what is the change? That's why we need a new symbol, because the change is a different value. Delta y is 20, right? 5 to 25, how much you have moved in your journey is only 20, because you already moved 5 in the beginning, and from there only we started measuring, right? I didn't want to find out the change from 0 to F. I wanted to find out the change from B to F, right? That's important. And therefore now we have delta y here, change in y, right? Now we can put this whole thing together and get a proper mathematical way of writing our most famous quantity that we got from this lesson, which is the rate of change of y with respect to x. So now this is actually the point of this whole lesson in many ways, because this quantity now and this quantity represented in this form is absolutely crucial for us as we go forward in our journey of mathematics and science and seeking truth, basically. Unfortunately, we have reached this after about 6 hours of this lesson. That's something I'm working on. Brevity is something I'm always struggling with. But anyway, we are here now. And now that we know we've introduced ourselves to the delta notation, we can go back to our good old quantity, rate of change of y with respect to x. And whenever you see rate of change of y with respect to x, what you're trying to say is how much does y change when x changes by every 1? How much does y change per unit change in x, right? So you're relating the change in y to x, right? To the change in x rather. Therefore, we use the phrase with respect to, right? And we know that the calculation for that is the total change in y in your experiment based on what journey, which point to which point you are going, divided by the total change in the x value or the x coordinate. Now, we don't have to keep writing these long sentences. We can now use this clean and crisp notation as change in y delta y, change in x delta x. So basically, whenever we talk of rate of change of y with respect to x, we basically say delta y divided by delta x, or delta y by delta x. And this can be extended to any quantity, right? Rate of change of any one quantity with respect to any other quantity is delta of the first quantity divided by delta of the second quantity. In this case, we are using the letters y and x. As I said, this is actually the point of this whole lesson in many ways. There are other aspects as well, but this is the main thing, because as we go forward, we will see how we use delta y by delta x in a multitude of ways to figure out many, many wonderful things about the world around us. So that's it for this gargantuan mammoth lesson. In the next class, we will look at a few more interesting properties of the graph that we've developed and build on the other tools that we've already discovered and see how we can make our lives much, much easier, simpler, and more fun in many ways. I'll see you very soon. Namaskaram. In this bonus section, what we're going to do is a little bit more of reflection. And what do we mean by reflection? We're just going to take a brief, quick look back into everything that we discovered in the course of this lesson and try to identify from looking back what were the methods that we used to discover all these truths that we found out. This is a part of a very important larger field of study which we refer to as epistemology. Now it's a big word, but basically in simplest form, epistemology refers to finding out how do we know what we know. What are the proper methods? What are the methods that work to give us true knowledge, right, about the existence around us and the existence that we are ourselves, right? So how do we know what we know? What are the methods that we use to get true knowledge and how to separate them from methods that might not give us true knowledge about what is actually happening in real life. This is very, very, very important, because then as we study this field deeper and deeper, we get better and better ways to find out what are the different ways in which we actually get true knowledge and truth, right? So this is part of that larger field. Now, this is particularly relevant to students who are doing the IB program, grades 11 and 12, because you guys have a subject which is absolutely fascinating, which in other words is basically just epistemology. It's referred to as TOK, or theory of knowledge, right? Theory of knowledge is basically part of epistemology. Basically, we look back and we see from all the ways in which we obtain knowledge, how do we actually obtain real knowledge, right? What are the methods that work? What are the methods that don't work? Why does some method work? Why does some method not work? When can a certain method be applied? When can a certain method not be applied, and why? All of these basic things to help us get better and better ways to find out truth, because that's what this whole thing is all about. So this part is quite relevant to students who are doing the IB program and who are doing TOK. You have your TOK essay and stuff like that. Now, most students are not very excited about the TOK essay because of your deadlines and everything, but actually if you kind of take the academic stress out of it, it's a very, very interesting and very important subject, because it's all about ways to find out truth. So basically we're going to, in short, apply a TOK approach, an epistemological approach to what we have discovered so far in our mathematical lesson, right? So let's do a quick look back. Now, just to see what we did in this actual situation, as always, we started from a real life experiment, right? We started from a real life experiment, we got the data from there, and then we plotted the graph, you know, the whole spiel, right? Now, at the beginning of this lesson, what did we do? We first started off with the 6 plotted points, right? The 6 original plotted points. I started from something very, very clear, actual data, actual numbers, right? I'm not looking for any patterns yet, just the actual numbers, the 6 points, right? And then when we put them on the graph, we were trying to identify why those 6 points were on the same straight line. And then how did we do that? We saw that when we go from the first point to the second point to the third point, I'm going exactly in the order of the points. I'm not jumping from one point to another plotted point, okay? I'm talking about the plotted points. Not only am I talking about the plotted points, I'm also going in a very specific order. I'm not jumping from one plotted point to the other just yet. So it's very, very concrete, very, very clear, right? So you start from A and B and C, you go to B, C, D, E, and what we realized was that the reason they all lie on the same straight line is because when I go from A to B, and then when I go from B to C, and then when I go from C to D, in each case, the amount the X is changing and the amount the Y is changing was the same, right? From A to B and B to C and C to D, the X always changes by 1 and the Y always changes by 5, and therefore we were able to see why that causes the same angle, and therefore they are in the same straight line. Now, there was nothing wrong with that. The only problem was that was very narrow. It was like a pair of handcuffs in many ways, right? Because that only allowed us to see this picture in a very specific way. We had to see only the 6 plotted points, and we had to not just see them only those 6 points, we had to go from one to the immediate next to the immediate next. We couldn't just see what's happening if I jump from one plotted point here to another plotted point far away. And certainly it also never told us anything about all the other millions of points on the line which are not plotted, right? So it doesn't give us a big picture. It only gives me a very step-by-step picture. We use the example of Frodo Baggins, right? Walking to put the ring in the fire, step by step by step by step. It doesn't tell me about the larger path, only tells me the next step. You feel like, a horse with blinkers, right? So you want to get a little bit more liberating. You want a larger picture. And we were able to do that when we saw this a little bit deeper. The second part of the lesson, what we saw was that you don't have to actually take the points, the plotted points in order. You can actually start seeing that there's a larger pattern actually forming, right? Wherein we saw that we took points which were plotted but not consecutive. We took, for example, points B and C, and then we went to C and F, right? And then we did the whole analysis over there, and we found out that what's more important than how much X is changing and how much Y is changing was what was common to all these plotted points was that regardless of how much the X changes and how much the Y changes as I go from one plotted point to the other, what was actually common is the rate at which Y was changing with respect to X, right? So you can go from one plotted point to another plotted point very far away, right? Therefore, because you're going to such, you're skipping from this point to that point, maybe the amount that X changes is not going to be 1, right? And similarly, the amount that Y changes won't be 5, like it was when I went from point to point in the same order. The amounts may not be 1 and 5, but the rate at which it was changing was, it was changing by 5 whenever X changed by 1. And that being common between the plotted points made sure that the plotted points were all on the same straight line. So we're in many ways saying the same condition, right? But instead of thinking it of in that very narrow way as point to point, amount of change in X is 1, amount of change in Y is 5. Next point, amount of change in X is 1, change in Y is 5. We're saying the same thing, but in a bigger way, saying don't worry about the amount of change. What is common is the rate. So the amount may not be 1 and 5. It could be 3 and 15. But what is common between 1 and 5 and 3 and 15 is it's changing at the same rate of 5 per unit, right? And that is why they were on the same straight line. Now we've got the first level of freedom, right? Now I don't have to go from point to point in this order. I can jump from any plotted point to any other plotted point, because now I'm thinking more in terms of rates of change as opposed to the total values of the change. And then we did a further sort of liberating move where we extended that from the plotted points to all the other random non-plotted points on the line, all the other infinite points, and we saw clearly that once we identified the correct patterns, we saw that we could quite confidently extend this and say that for any 2 points, plotted, unplotted, consecutive, spread far apart, doesn't matter. As long as those points are on this particular line, the rate of change of Y with respect to X will be 5, right? And that gave us a very broad condition, a very big view of the whole thing. We use the term abstraction, right? We're not talking about the individual numbers now, 1, 5, etc. We're just looking at the same thing in a bigger way, right? Called an abstraction. We got it from real life, but now we are seeing it in a different way, in a bigger way, called an abstraction. And what was that abstraction? The abstraction was that for any 2 points, as long as they're on this straight line, the rate of change of Y with respect to X will be 5. And that also gave us the same thing in an even broader way, where we realized that for a straight line, if there is a straight line, then you can rest assured that you can take any 2 points on that line, and the rate of change of Y with respect to X from any one point to any other point on that line, as long as they're on that line, it will be constant. It will be constant. And in the case of this line, that constant was 5. Right? So you see another level of abstraction, right? Not only did we find out that it was 5, we realized that 5 is only for this line. You could have another line, maybe the line goes like this, and we'll see examples of this later on. Another line goes at a different angle. For that line also, the rate of change is constant for all the points, but just that value may not be 5. That value may be something else. You have a line like this, the value may not be 5. It could be something else, right? Any other number, but it's constant for that line, constant for this line. So we see a larger pattern that if it's a straight line, the angle has to be the same, the direction of travel has to be the same. If direction of travel has to be the same, rate of change has to be the same, right? But what is the value of rate of change? For this line, it could be one value. For this line, it could be another value. For this line, it's 5. Right? So again, it's what we refer to as an abstraction. But very importantly, we got the abstraction from the actual concretes from the real life experiments by identifying the patterns. Once you identified the patterns, then you're not worried about the individual numbers. Until then, you had to take care of the individual numbers. You have to say 1, 5, 2, 10, etc. Then you say, okay, rate of change is 5. Then you say, okay, rate of change is constant. And in this case, it's 5. So you see, we're getting bigger and bigger and bigger. But at every stage, it's very, very much connected to the lower level. We're not making stuff up in between, right? That's very important. There's a constant chain, right? And that chain is what we have shown over here, right? This is what we have done. This is the epistemological reflection. Oh, lovely, big words. Epistemological reflection of what we have done, because this will now give us a method that we can start using in other mathematical situations as well, right? To get more and more truth. So if you want to show this in a very simple diagram, this is basically what it is, right? We started with the real life experiment. The real life experiment gave us actual numbers, values, what we refer to as concretes. Then you look at the concretes and you see what connections they are having, right? You just look very, very neutrally. What are the connections? And then you start getting the bigger picture, right? You get the theme, you get the idea, right? And that is the abstraction. And all the individual numbers are just different cases of that abstraction. To borrow an analogy from English, we have the English proverb, to see the forest instead of the trees, right? So basically what that means is, you're inside in the wilderness and you see this tree and you see that tree and you see that tree and you see that tree and a plant here and a shrub here. Now if you actually look, each tree and each plant, they are different sizes, different shapes, the leaves and flowers and the fruits, everything smells differently, right? But there is something common to all of them, right? They start from the roots and they have some sort of a bark or a stem, and then they have some sort of leaves. Maybe the actual shapes and sizes are different, but the general idea of what's happening is the same. They are living beings and their seeds fall and they grow again and then they die, and those things are pretty much the same, but how it actually happens are different, right? So these are the concretes. But then when you go up and say, okay, it's basically a forest, and inside this forest you have different versions of plants and trees, etc., right? But they belong to that same family. So in this case, the trees and the plants, that's the real life, that's the concretes. From there you see the patterns, right? And then you group them, right? And that is the abstraction. But at any stage, you should be able to, if you want to check whether your grouping and your abstraction is right, the best way to check is check it back with real life. So when you go from the abstraction and you come back in the opposite direction, does it still get you back the original concretes? Do you still go back to real life? Right? Or is there a breakage in the link somewhere where you have made up your own stuff? That's dangerous, right? So we can always check from the forest. You can get off your helicopter and go down, and you can actually see the individual trees, right? So from the abstraction, you should also be able to, whenever you need to, as a check, come back to the real life experiment, go to the concretes, and again see how the concretes give you the abstraction. So this is like a loop that is a good way to check, right? And the same thing can be applied to our experiment as well. From the abstraction, from the overall thing that we said that for a straight line, the rate of change is constant, right? We can check for this line. Is it constant? Yes. What is the value of constant? It's 5. Draw another line. Check, is it constant? Yes. What is the value of that constant? May not be 5, maybe something else, but it will be fixed for that line. For another line, you can check, right? And therefore, you can check whether your entire process of gaining knowledge is right or wrong. And then if it's right, you can start applying the method to other such situations, right? So this is epistemology. Now, where this is extensively used is in all your sciences, right? Whether it is physics, chemistry, biology, all your scientific concepts or scientific laws essentially come from this method. Today we refer to it as the scientific method. In university you will study it as RM, research methodology, right? How do we get knowledge, basically, right? And this basically what is happening in all your sciences. You start as always from the real world, because the ultimate test is we refer to as RWOT, the real world out there, right? You can come up with all these fancy explanations in your head, but does it actually match in some way with the real world out there? Clearly, without any doubt, right? So R what is another way of thinking about it, right? So we start with science experiments, the actual experiments, whatever the experiment is, right? And that gives you the raw data. The raw data means just the numbers, right? We haven't identified any patterns yet. We've just got the numbers. Then when you look at the raw data, you start identifying what are the patterns, what is the cause, what is the effect, right? So now you're starting to look at the numbers, but you're not trapped by the actual values. You're trying to see what the cause is, what the effect is, what is the pattern, what is the basic story that's happening, wherein the numbers are just individual cases of that basic story. Once you identify that, that gives you the overall abstraction. In that case, we refer to it as the law or the theory, right? Where, okay, this is the explanation. This is what is happening. This is the forest. Right? This is the abstraction, and we saw one example of the abstraction here. Now, the abstraction today could be all our scientific laws. For example, Newton's laws of motion in physics, the theory of evolution in biology, the atomic theory in chemistry, theory of relativity, etc. So these are your final laws, right? But how have they come? They have come from this process. So you can always go back and check, right? They have come from the real life experiments or experience, right? In some way, it's clear, and then we have seen the patterns, we've identified what are the causes, what are the effects, and then we're saying, okay, this is what is happening, this is the law. Now, what is the advantage of having this law like this, or having the theory like this? The advantage is that once I know what is happening, right, I don't have to keep testing it again and again and again and again, right? So for example, once I discover the law, once I discover what the basic law is, I don't have to do the same experiment in another country or the same experiment tomorrow in a different city, right, at a different time of the day. I know that as long as the same conditions are happening, the same basic idea is happening, the same causes and the same effects, maybe the individual numbers from the experiment done over here will be different from the experiment done in another country or on another planet. But the same connections are happening, the same method is happening, the same causes and effect are happening. So the same result will happen, just that the numbers might be different, right? Basically very similar to what we are saying here. Once I know that for a line, the rate of change is constant, right? I don't have to keep drawing infinite lines and again checking. I know that in all the other lines, the same basic thing is happening, right? The direction of travel is the same. If direction of travel is the same, the rate of change has to be the same, because that is what determines the angle. That is what determines the direction. So if that's true for this line, it will be true for every single line. It's just that the value will be different from line to line, right? So that's the beauty of it. Now I can build on this knowledge and find out deeper things. I don't have to spend the rest of my life testing it for every single line, right? But when I do have a doubt, at any stage if I have a doubt, I can, if I want to, I can take that law and go back to real life and check, right? That test is always available, right? So if you do it right, you will get the law, right? You don't have to keep testing it. But as a sort of a bulletproof way of making sure that it's foolproof, you can always check back. So you can complete this loop, right? So this is what we refer to as the scientific method. This is basically from the study that we refer to as epistemology, and you can see now how useful this whole field is. Now, just to make this process of gaining knowledge and the study of this process of gaining knowledge, what we call as epistemology or theory of knowledge, just to make it a little bit clearer without using a mathematical example. So this is just a way of doing the same process of going from concretes, that is C, to abstractions, that is A, and then also seeing how we can come back to the original concrete, that is A to C. How we show this process, we are trying to now show it in a non-mathematical example, a sort of more day-to-day real life sort of an example, which does not involve mathematics, just for us to understand the picture of what we're trying to do, the map, the pathway, which then can be applied to any situation. So I have taken a case of things that you eat, basically, right? So let's start right from the lowest level. That is, let's start from real life, what we can actually see in front of us, concrete data, right? So what I mean by that is, let's go to the innermost part. So as you can see this diagram, we have big boxes, smaller boxes, and inside the smaller boxes, even smaller boxes, right? So that is key to this entire process. Here I start off with this box here, right? Now this box here is using the letter A. Here A stands for apples. Now let's start from that situation. Now if you, in your house or in the market or whatever, if you go and look at the apples, right, no two apples are actually identical, right? If you actually look at them, each apple will be a different shape, a different size, sometimes a different color, sometimes they are bigger, they are smaller, and they're bent up in one shape and the other, and the textures are different. So actually speaking, if you have 100 apples in front of you, and if you look at each of the apples, they're all quite different from each other, right? So those are different concretes, the data, like numbers, right? They're all different from each other. But there is something common. There is some pattern there that's common to each of these 100 fruits that you're seeing, right? And what are some of the things which are fundamentally common? Well, if you bite into one of them, you will largely get a very similar taste. The way it feels in your mouth, again, is largely similar. If you want to go a little bit deeper, if you look at the seeds, again, the shapes and sizes of the seeds might be a little bit different. But again, overall, they have a similar color, they have a similar feel in the way they feel in your hand. And if you go a little bit deeper and you go back to the original plants, the different plants that give you these particular 100 fruits that you're calling apples, they might look different from each other, but again, they grow in very similar ways. They have a similar root structure. Maybe the amount of time they take to give you the fruit, etc., is similar. They are the same kind of plants, but different shapes and sizes. But the way everyone behaves is pretty much the same, right? That is why you can, in that situation, look at those 100 fruits that you have and ignore the small changes in shapes and sizes. Ignore the differences in measurements from one concrete to the other and say, okay, they're all different individual shapes and sizes, but they still have something in common, right? In terms of the way they taste, in terms of the way they feel, in terms of the way they're grown. And if you want to go even deeper, we can, thanks to modern technology and evolution, biology and stuff like that. And you can say, well, they have a very similar genetic structure, similar chromosomes or DNA with minor changes, right? So something is common. And therefore, we can ignore the local measurements, the differences between fruit to fruit, and call them all apples. So this is your first abstraction, right? Inside this box, I could have 100 different apples, but they're still apples, right? So when I say apples, I'm not talking about any one apple. I'm talking about all, right? In many ways, you can say, I'm talking about nothing, but actually I'm talking about everything, right? So when you say apples, it doesn't tell you about one particular apple, but it just tells you that this is the overall class, and inside that class, there could be many, many different individual apples, many different concretes. This is your first abstraction. You can do the same thing for all the fruits which look and feel a certain way, even though from fruit to fruit there could be a change in length and size, etc. You will now call them bananas, right? And it's very important. You will not use the word apples to describe this class, right? Because if you look at the apples and if you look at the bananas, now when you look at an apple and you look at a banana, just like within the group of apples, from one apple to one banana, again, the shape is different, the size is different, how it feels is different, right? But in that case, you just can't ignore the differences and still call them all apples. Why? Because the difference between an apple and a banana is not simply the surface level, oh, it's just a different shape and different size, but the fruit is basically the same. It's not, right? A banana tastes, looks, feels completely different to an apple, right? If you imagine a banana in your head and imagine an apple in your head, they are quite different. It's not just a difference in, oh, it's the same fruit and a different shape or size of it, right? It's not. And if you want to go deeper, the kind of tree or plant that you get that you need to grow a banana is quite different from that of an apple. The way that plant grows is quite different. When it sprouts and when it flowers is completely different from that of an apple. The conditions it needs are completely different. And if you want to go deeper, the genetic structure, the chromosomes and the DNA are dramatically different from the apple. They're just not variations on the same theme, right? So there is something different. So while you make the group or the abstraction apple, you have to understand the scope of that abstraction. You cannot extend that term apple to anything blindly, right? I cannot extend that apple and call all the bananas also apple. Likewise, I cannot extend the term bananas to the apples, right? So when you make an abstraction, you have to be very careful as to the scope of that abstraction. You just can't blindly apply it wherever you want. You have to see where the differences are just differences in shape and size but the same overall story, or where the differences are much deeper than that, something significantly different, right? You have to distinguish between the two cases, right? So when you look at the bananas, from banana to banana, there could be many differences, right? But there's something common between all the bananas in terms of where they taste and etc. So we can call them bananas. That's the abstraction. Similarly, M for mangoes, another abstraction, right? But the abstraction or the class apples cannot be extended to include bananas. And likewise, mangoes cannot be extended to include apples or bananas. They are separate classes. But there is something common. If you now look at the apples, the bananas and the mangoes, you have the apples here, the bananas here and the mangoes here, right? They're actually quite different from each other in terms of the way they look and the taste and the DNA and the chromosomes, and they're quite different. But there is something common between these three groups that you've seen. What are those things that are common? Well, whatever plants that do grow them, they fall, and you can generally take them and wash them and then you can directly eat them, right? And generally when you eat them, they are pretty sweet, and if you keep them out on your basket, they stay for some time, and they have some similarities that in the way they taste, generally on the sweeter side, and the way they are grown, even though the conditions might be different, but generally they grow and it falls and you pick it up and you can eat after a little bit of cleaning, right? So while they are different from each other, there is something fundamentally at the bottom common, right? And this is the word that we use. The word that we use is fruits, right? They fall into the category of fruits. So now apples, bananas and mangoes become your concretes. These are concretes. These are quite different from each other. But now when you are thinking of what is the overall thing that is common to them, you ignore the fact that the apples are different from bananas and the bananas are different from mangoes. You're just seeing, okay, apart from their differences, what is something that connects all of them? They generally fall in one category, which is fruits. So now A, B and M become concretes, and now fruits becomes the abstraction. Earlier, the individual apples were concretes and the apple was the abstraction. Individual bananas were concretes, the term bananas was the abstraction. Now, what was the abstraction earlier becomes the concrete. A, B and M becomes concretes, actual data, and now you group them together in the category fruits, right? You're not going to extend A into B or B into M. They are separate inside, but you can put them all in a larger box called fruits. This is your next abstraction. That's the same thing I've done over here. Whatever we've done over here, you can repeat here between the vegetables, right? The vegetables is like the fruits, the abstraction, right? Inside that, of course, you have potatoes for P, B for beans, and S for spinach, right? Just like the three fruits, these are significantly different from each other, right? So these are again the lower level abstractions. And if you go right inside, you're back to real life. Inside the potatoes, you have individual potatoes. Inside the B, you have individual beans. And inside the S, you have individual, bunches of spinach of different shapes and sizes, right? But there's something common between all the potatoes, so you say P. Something common between all the beans, so B. And similarly for the spinach, S. Now, the P, B and the S fundamentally are different from each other. The potatoes are different from beans. Beans are different from spinach. But there's something that they have in common, right? They all are edible. They all Unlike the fruits, when they come out, some of them come as roots and some of them come as leaves, and you can't just directly take them and wash them and eat them. Generally, you might have to do a little bit of treatment, some kind of cooking or boiling or something, which you generally don't have to do for the fruits, right? So they are edible, they're different from each other, right? And they might have different DNA, etc. But what they do have in common, right, what potatoes, beans and spinach have in common is that the way they cooked, and also they all may not be sweet, right, like the fruits. So they all taste a certain way, they're made a certain way, the plants grow a certain way. So you can now group them as vegetables. So when you say veggies, the veggies are quite different from the fruits, right? These are two separate abstractions, two separate cases. So you don't extend veggies into fruits and don't extend fruits into veggies. Inside the veggies, there are different vegetables. Inside each vegetable box, there are different versions of that same vegetable. So same way, we've done the same process over here. Similarly, I've done that for the meats, right? Now, if you start right from the beginning, you see, for example, here C stands for chicken, F stands for fish, and P stands for pork. You can include any other meats you want. Similarly, here also, you can include other vegetables and other fruits. I've just taken completely random examples. Now, when you look at the same thing, right? Individual chickens look quite different from each other, right? But again, there's something common between them in terms of their DNA and how they behave, etc. How the meats taste themselves, right? The cooking procedure, etc. So you have C, right? Chicken. Similarly, fish, quite different, right? So you put them in the category of fish. Then pork, quite different animal altogether. Put it in the category of pork, right? But what is common between C, F and P, right? What's common is they're all edible once they're cooked. It's edible, and again, they generally don't taste sweet, right? And what's common over here is that they come from animals, in the sense, for example, compared to the fruits and the vegetables, the chicken, the fish and the pork, that is the pig where the pork comes from, they are mobile, they move, they have a more developed nervous system, they have a significantly different genetic code from vegetables and fruits, right? So there is something common to all of them, that is they are meats, that is they come from animals and not from plants or trees like the fruits and the vegetables. So there's something common to all of them, right? Inside, the animals are different, the meats are different, chicken, fish and pork are quite different, but they all come from, mobile animals with a more developed nervous system, a completely different genetic structure, significantly different at least from vegetables and fruits, right? So you use the abstraction meats, right? So you can do this on your own. You can see in each box, start from the innermost box and see how you've come to the outermost box. Do that here, and then look at these three boxes together, right? So now these three boxes become concretes, and see what abstraction can now be formed. And that is the last that we're going to go to right now. If you look at the fruits, you look at the veggies, and you look at the meats, them as individual classes, they are quite different. You cannot extend the term fruits to the meats. You cannot extend the term meats to this blindly. They are completely different abstractions, right? But there is something common between fruits, vegetables and meats. What is that? There are so many differences, but one thing that's common to all of them, maybe because of the genetic structure having some similarity, or because of the way we are built, we can find out. But what they have in common is all of them are edible by a human being. That's one commonality, right? All of them can be eaten. All of them can be digested and can contribute to our nourishment and growth, etc. Individually, fruits are different from vegetables and meats. Inside, the individual fruits are different. The individual vegetables are different. The individual meats are different. Inside a given fruit or a given vegetable category or a given meat category, the individual members can be quite different from each other, right? But finally, when you come out, they all can be included as an overall abstraction of food, edible, right? And again, you can see now for the abstraction food, the concretes, that is the individual members that you connected to get food, are fruits, veggies and meats, right? The fruits, veggies and meats were abstractions for the what members were there inside. For the fruits, A, B and M were concretes and that became fruits. For veggies, P, B and S were concretes, that became veggies. For meats, C, F and P were concretes, that became meats. right? And then if you go inside, what were earlier concretes? For fruits A, B and M were concretes. Now, but you go inside the fruit box, A, B and M are now abstractions, right? Apples A is the abstraction for all the individual apples inside. Bananas B is the abstraction for all the individual bananas inside. So you see this happens like a cascade, right? The concretes for one stage will give you the abstractions. The abstractions will become concretes for the next abstraction. Then these abstractions will become concretes for the larger abstraction. So you can go up the pyramid or down the pyramid. So this is basically what it is. You can include one more if you want. In the group food, this is basically everything that's edible, right? You can distinguish this abstraction from another abstraction, another class of non-edible items. So you can put your plastics over there, you can put your metals over there, all your industrial chemicals can be put over there, right? That's another class, non-edible, right? So the food cannot be extended to them, and those, that term non-edible, that term cannot be extended to the food because they are significantly different. And we can go on like this, right? So the three important points to realize from this process, right, that can be summarized by here, by looking at this diagram. You're going from the concretes to the abstracts. When you're going from concretes to the abstracts, you're just seeing the patterns that are common between the concretes. And then when you identify that, you can ignore the individual changes in their values or in their shapes and sizes, and you can make the abstraction, right? You can do that further and further. At any time, if you want to check whether this abstraction is correct, this step is correct, you should be able to go from that abstraction and come back and land up with the actual concrete. It should be able to come back to real life, so that way you can check at any stage in the process, have you made a class or have you made up something that doesn't really exist, right? So you can debug the process, and you can show that over here. You can do it right from food itself, right? When you think of food, you're like, okay, food, but it doesn't tell you anything in particular, right? Okay, it tells you that it's in the class of food, so it's definitely not plastic or metal, right? It's food, but it doesn't tell you what in food. Now you can go inside food and you can think, is it a fruit? Is it a vegetable? Or is it a meat? Again, it doesn't tell you what it is, but it could tell you one of them. Let's say you go into fruits, right? You still don't know what you're eating, right? So you still haven't come back to real life. But you're getting there, you're getting closer, right? It's like a GPS system, you're narrowing down on your target, right? So you have fruits. Now, which fruit could it be? It could be any one of the fruits, apples or bananas or mangoes or whatever else, right? Let's say apples. Even when you reached apples, you still don't know what you're eating, because inside apples, there could be many apples, right? Then you go inside apples and then you take one, and then you're holding that one apple in your hand. So at the end of the day, if all of this really is true, you should be able to come back and finally be actually having something real. It should match with something in real life. It should go back to your actual experiment, and you should be able to check it and test it without any doubt, right? So that's the second point. So you can form all your abstractions, but make sure that at any point, if needed, you can come back and check it. It's a foolproof way, right? And the third important point is, when you make an abstraction, you must be careful not to blindly extend that classification, that abstraction, into any and every case, right? You can't blindly extend fruits to vegetables, right? You can't blindly extend vegetables to meat. You can't blindly extend the term food to include all things which are not edible as well, right? So the scope of an abstraction has to be considered very carefully. So this gives you a good overview of how our knowledge building process works. Now this diagram is a very similar diagram to the abstraction we did for our fruits and vegetables, etc. This is just a summary of what we did in our experiment, in our mathematical case. We've already discussed this, so I'll quickly just go through it, and let's use this to think of it as a map to what we did, right? So what did we do? The PP here stands for the plotted points, that is the 6 plotted points in the order of plotting, A, B, C, D, E, F. This of course came from the real world experiment. So these are your first concretes, right? So when we did the whole study of this particular situation, we started from the plotted points in the order, right? We went from point to point and we said that From each point to the next point, x changes by 1 and y changes by 5. That was the lowest level concrete. Then you looked at it deeper and you were able to extend it. That's why that's shown by this arrow. I'll come to the reverse arrow very soon. Now we're going in this direction, okay? So from PP in order, we extended it to the plotted points, PP random. That means I was able to jump from B to F or C to E, right? Because then I realized that it's not important or not as important to think of it as x changing by 1, y changing by 5. What's actually the larger idea here is that between any two plotted points, the rate of change of x is the same, of y is the same with respect to x. That is how much y is changing per unit change in x, even if the actual numbers are different, right? So we were able to extend this into any two random plotted points, right? That's what the second stage is, right? So it's kind of like one abstraction. Then we are able to realize that that same concept, that same condition can now be extended to any other 2 points on the line. They need not even be plotted. For any other 2 points, as long as they're on this straight line, the rate of change of y with respect to x is 5. And that gave us the condition for this given straight line. The condition was that if you have this particular line, you can be sure that you can take any 2 points on the line and the rate of change of y with respect to x for the given straight line will be 5, right? That was the next abstraction, looking at it in a bigger way, right? And then we use that to generalize and to extend it to any straight line, right? And we realized that what's actually true here is that you can take any straight line, and as long as that line is straight, you can rest assured that you can take any 2 points on that line, and for that line, the rate of change of y with respect to x as you go from one point to the other will be constant. It will be fixed for that line. Now, that is what I've shown over here. In the case of this line, that value is 5. It's part of a larger idea that it's constant for a straight line. For this line, it's 5. For this line, it could be something else. For a line like this, it could be something else. And we'll see more on that later. But the general common thing is that it's constant from straight line to straight line. The actual value depends upon which line. That actually is a good segue into seeing how we can come back, right? You can actually now go from the abstraction and come back to real life to check is there any missing link along the way, or can I actually connect it straight back down to my original experiment, and therefore it's true, right? You can start from any straight line. For any straight line, the rate of changes of y with respect to x is constant, right? In the case, now this is where the reverse arrows become useful. I'm coming back, right, from the largest abstraction to the smallest or the lowest concrete. For a given state, then it's constant. For the given line, that constant value is not 7, 8, 3, 0.5, it's 5. That'll narrow me down onto this line. That will apply to any 2 points on this line, right? If it applies to any 2 points on this line, it will obviously apply to any 2 randomly plotted points, any 2 of the plotted points chosen randomly, right? And therefore, it will also apply to any 2 of the plotted points chosen in the order, that is A, B, B, C, C, D, in the order in which they appear in the experiment. It will also apply. So I can go step by step and see how from the largest abstraction I can still reduce it down to the plotted points in order. And what are these plotted points in order? The plotted points in order are actually stages. They are stages in the actual experiment, and this will connect you back to your car on the road. It connects you back to real life. So in this case, this abstraction clearly works. For those of you who are interested in taking a deeper dive into what we've discussed so far as epistemology, which is how do you know what you know, and how do we distinguish between what is true and what is not true, you must check out the work of a great contemporary, legendary philosopher who goes by the name, well, her original name is Alice O'Connor. Many of you may not know that name too well. Her pen name has made her more famous, and that is Ayn Rand. And of course, she's famous for a lot of works of fiction as well. But if you actually look into the work that Ayn Rand has done on how we gain knowledge, theory of knowledge, epistemology, how do we judge truth, etc., you will find a whole other treasure trove of stuff. And I'd like to recommend one particular book which had a profound impact on me and how I look at the world around me in terms of, as a seeker of truth, how do I know what's true and what's not. The book that I would recommend is Introduction to Objectivist Epistemology by Ayn Rand. This is a great starting point. It's intense, it's heavy, but if you actually get into it, it's profound. It's absolutely wonderful. This is a great starting point for those of you who are interested in all of this. And as a follow-up to this book, pretty much on the heels, being influenced by the work of Ayn Rand, if you want to take a deep dive into the process of epistemology, specifically applied to how knowledge was developed in the field of physics, right, which can then be used as a base to understand how it happened in other fields as well, I suggest the book The Logical Leap. The Logical Leap by David Harriman, another life-changing book which I thoroughly enjoyed. I've probably read it about 50 times. Heavy, intense, but absolutely wonderful. These two books are great starting points for any of you who wants to dive deeper into all of this. I have included the Amazon links for both of these books in the description, so you can check it out from there and pick it up if you like. This is not part of this affiliate income thing that is happening on YouTube, because currently I'm not eligible for that, but who knows, it can happen in the future. But right now this is purely from an academic perspective to help you guys get started on this journey. And as you can take it forward, you can find many other wonderful books and resources which can further deepen your understanding of all of these ideas. Namaskaram.